Hi everyone. So today we'll be discussing on the topic Holm-de-Lichtenberg-Thorup algorithm. Yeah. So let's see what the definition states. Yeah. So HDT or the Holm-de, this one Lichtenberg-Thorup algorithm. What it does, it maintains a spanning forest. Just remember this. It maintains a spanning forest of a dynamic graph. Yeah. So that's what it does. It maintains the spanning forest of a dynamic graph under edge insertions and the deletions. The main thing will be making use of it for the edge insertions and deletions itself. So we'll be going with the simplified this one algorithm actually, Holm-de-Lichtenberg algorithm. So the entire algorithm, let's implement that one in the this one problem that we consider. Yeah. Anyhow, we will be getting to know the whole algorithm. Not to worry. So again, HDT maintains a spanning forest of a dynamic graph under edge insertions and the deletions, answering connectivity queries in big O of log square n. Answering the queries in big O of log square n. Amortized time. It uses hierarchy of Euler-Tour trees, right? What does it use? It uses the hierarchy of Euler-Tour trees. If you remember, we have already discussed the Euler-Tour trees algorithm, right? So within the trees based algorithm, if you don't know, you can just check the 150 algorithms playlist or tree based algorithms playlist in the Java. You can do that. Yeah. So it uses hierarchy of Euler-Tour trees across big of logarithmic n levels to efficiently detect the replacement edges after the deletions. So that's what it does. Again, why it uses the ETT or the Euler this one tool trace. So it uses Euler this one tool trace this one across different levels to efficiently detect the replacement edges of the deletions. So this one we'll get to know when we write the algorithm clearly. So this is the main part of the algorithm actually. So this you'll get to know, sorry, you'll get to know this one while we discuss the algorithm or this one approach basically. Now we are done with the definition part. So you have to remember this part at any cost. Now let's do one thing. Let's discuss the algorithm or let's discuss the approach so that we can just move on with the further things. After discussing the algorithm, let's write the code if everything goes well. If we get the desired output, then we can discuss the complexities for the code that we have written. First, let's discuss the approach. Let's do that. So let's continue with the algorithm. So the first thing here, yeah, first thing, the graph consists of the nodes 1, 2, as well as 3 and 4 respectively. Just give me a second here. 1 second. Yeah. So the graph consists of the nodes 1, 2, 3, and 4 respectively. I'll just show you the graph now itself. Just look at the graph. This one, the first graph actually. Yeah. 1, 2, 3, and 4 respectively. Right. So the second one here, edges we have 1 to 2, 2 to 3, 3 to 4, as well as 1 to 3. You can clearly see here again the first graph. We have the edges 1 to 2, 2 to 3, 3 to 4, as well as the dotted lines that has been connected. You can clearly see the dotted lines from 1 to 3. Yep, from 1 to 3. Yep, so this is the graph actually. Next, let's do one thing. Let's move on with the main things. What is the core idea of the algorithm here? Let's discuss the core idea. So we will assign each edge a level actually. Yeah, we will be assigning each edge a level 0 to logarithmic n, right? 0 to log n. Yep, so first step is very easy. What we are doing here, we are just assigning the each edge a level. That's what we are doing. Then tree edges, whatever the tree edges that we have, that they form the spanning forest at each level. As we have the different levels, see, from 0 to 1 it will be different, from 1 to 2 it will be different, from 2 to 3 it will be different, and 3 to 4 it will be different, and again 1 to 3 we have one more edge that will be different as well. Yep, so these tree edges form the spanning forest at each level. Non-tree edges are stored at their assigned level. It's as simple as that. Non-tree edges, they are stored at their assigned level. Yep, it's as simple as that. Now, let's move on with the main part. See, first we will insert 1 to 2. First we have 1 to 2. Sorry, 0 to 1 we do not have. We have from 1, right? Level 0. First we have from 1 to 2. This part. Yeah. First we have, first we will insert 1 to 2. So now we have the tree edge 1 to 2 at the level 0. First level, nothing but the level 0. The spanning forest would be initially 1 to 2. The edge 1 to 2. Yep. So this is clear, I believe. Next, let's move on with the next edge that we have within the graph, nothing but 2 to 3, this part. Yeah, from 2 to 3. So this time, this is the non-tree. Yeah, this is the non-tree. 1 second, just give me a second here. So now, yep, sorry for that. Let's move on with the next thing. So we have inserted successfully inserted 1 2. Now we were speaking of inserting 2 3. So we have the tree at 2 to 3 at the this one level 0 itself, right? Forest forms two things. One is 1 2 as well as the 2 3. I directly hopped into 1 3, I believe. So this is fine. Yeah, this one 1 2 2 3 is done. Now so this one. Now we have 1 2 3 actually. Inserting 1 2 3. Inserting 1 2 3 is non-tree because it creates the cycle. So we already have 1 to 2 to 2 to 3. So this one 1 to 2 we have from 2 to 3. And again from 1 to 3, it this one what it does, it forms a cycle. Quite obviously, you can just look at the graph. Non-tree, it creates the cycle stored at the level 0. And what we will do, we will delete 2 3. This part we will be deleting 2 3 this part. This, yeah, we'll be deleting 2 3. So forest splits. So the forest splits so that it doesn't form a cycle and it forms a this one what do we call, so that the spanning tree forest or the forest splits actually. Yeah, search for the replacement edge. We will be searching for the replacement edge at the level 0, and then we will find 1 2 3 and then reconnect. Yeah, what we'll do, we'll search for the replacement edge at level 0. If we have successfully found 1 2 3, then we will reconnect. See, the second graph actually, you can clearly look into it. This one, see, level 0, we have 1 to 2 1 to 2 to 3 3 to 4, this part. Yeah, 1 to 2 2 to 3 3 to 4 is fine, but 1 to 3 here I have shown you with a dotted line. This forms the cycle actually. We will be completely deleting this edge. So what we'll do next, this is level 1 after the promotion on delete. See, 1 to 2, this part actually we have completely deleted. So this part doesn't exist. 1 to 2 to 2 to 3, nothing but 1 to 3. So only we will be going with this part, 1 to 3 directly, and then 3 to 4. Yeah, then 3 to 4. This is the level 1 after promotion on delete, right? Or after delete actually, in simple terms. Yep. So see, we will search for the replacement. We have searched for the replacement and we have found the replacement actually. As we had found 1 to 3, then we have reconnected accordingly with what I had showed you on this one in the graph 2. So this is fine. Now let's move on with a key trick on the deletion. So the first thing here, when a tree edge at level I is deleted, when a tree edge at level I, particular level, yeah, when a tree edge, in our case, we deleted at the level 0, right? So 1 to 2, 2 to 3. So in our case, we deleted that edge and we directly moved from 1 to 3. When a tree edge at level I is deleted, so HDT or the Holm-de, this one, Lichtenberg-Thorup, what it does, it promotes the non-tree edges and searches level by level for the replacement. That's what I said, right? So that itself we are discussing again. That's it. We are just going with a key trick on the deletion part. So the smaller components get edges promoted to the higher levels to found, right? It's as simple as that. So that's what I said. This is mentioned. I have mentioned this one theoretically so that we understand this one clearly, right? So let's move on with the next part. So this is it for the algo. This is it for the algo. It's actually very simple. But basically, when we go for the this one pure implementation, it consists of many things. When we solve the problems, you'll get to know. When we solve the problem, or when we go for the pure HLD implementation, right? HDT, sorry, not the HLD, HDT implementation or HLT, however you call it, right? Holm-de, this one, Lichtenberg-Thorup algorithm. So the algorithm is heavy, but if you understand this part, actually, implementing the algorithm becomes very easier, right? Very easy, sorry. Yeah. Now, what does the Euler-2 tree does here? It represents the spanning forest. Yeah. Basically, what it does, it represents the spanning forest at each level as balanced binary search tree. Yeah. We have the knowledge on the balanced binary search tree. Nothing but at every level, the parent node should have two nodes, right? Two children actually. And for the binary search tree, the root node should be this one, greater than the left child, and the root node value should be lesser than the right child value. So this is the rule. We know this one, right? At each level, as balanced binary search tree supports, and it supports split, merge, this one query, these three operations: split, merge, as well as the query in big of log n per operation. What it does, Euler-2 tree. We have already discussed the Euler-2 tree algorithm. Yeah, we should be knowing this at this point of time. So Euler-2 tree, what it does, it represents the spanning forest at each level as balanced binary search tree, supports split, merge, as well as the query operations and big of log n per operation. So this is fine. Next, let's move on with the replacement at search. So here we'll check non-tree edges level by level. Then we'll promote the edges of smaller component. What we'll do, replacement edge search, we'll check the non-tree edges level by level, right? So that's what we did when I showed you the graph. Well, we consider this graph. We check for the non-tree edges level by level. Non-tree edges was this one basically. From 1 to 3, we had connected this one directly, right? This is a non-tree edge. So we'll check non-tree edges level by level. We'll promote the edges of the smaller component. That's what we did. Yeah, we directly considered 1 to 3, deleted the 1 to 2 to 2, 3, that edge. Yep. So we'll promote edges of smaller component. Each edge promoted at most logarithmic n times. Each edge, so this one we have to remember, each edge promoted at most logarithmic n times. So overall time complexity would lead to big of log square n amortized delete. So we can consider the time complexity as big of log square n. So this is fine. Yep, for the delete actually, amortized delete, I have strictly written that. So this is it for the algo. Yep, so this is it for the algo. Now let's try to articulate the same thing in the form of code. Yep, let's write the algorithm by making use of the Java programming language. Let's do that. So let's move on with the coding part. So the main thing here, so we'll be going with a HDT simplified as I've said. So we'll be going with the adjacency plus this one, spanning forest tracking. Yep, nothing but we'll be making use of the Euler tool tree actually. Yep. So this is fine. As I've said, let's do one thing. Yeah, I'll just go with let me import Java .util.star. So we'll be this one making use of the different utilities. So let me import this package. So within the main function actually, or HDT function, HDT method. So let's do one thing. Let's go with a data structure. So I'll just go with int n because we need number of nodes, right? So next, let me go with a list here. So I'll just go with a set. Set of this one. We are dealing with the integer, right? Integers actually. I'll just mention the integer over here. Let's go with a variable name adj. Next, let me go with a list of set. So I'll just go with the integer again. So let me go with the integer, and this one would be, let me go with 3 adjacency. Yep. So this is also fine. Next, let me go with int. I'll just go with a parent here, and let me go with a rank. Yep, parent and rank for the this one union find, right? So we'll be going with a union find for connectivity. So there we'll be making use of the parent as well as the rank. So and this one tree adjacency nothing but the it is for the spanning forest adjacency list, and adj variable it is just the full adjacency list, nothing but all edges. So first let's go with the constructor part. Let's initialize n nodes. So how can I write that one? So let me come out of this one. Sorry. Yeah, let's move on with the further thing. Sorry. I'll just go with public here. This one. 1 second. So let me copy this one. Let me do one thing. Yeah. Just over here. I'll just go with int n. Yep. So there are certain things that we need to initialize. I'll just initialize n. Then we have considered adjacency list. Actually, I'll just go with a new array list here. So I'll also go with tree adjacency. Let me assign the same here again array list. So let me go with a parent. So equals, so new int of size and rank also new int of size so this is also fine. Next, let me go with the for loop. Within the for loop, I'll just go with the same actually. I equals 0, I less than n, I plus plus. So within the for loop, what I'll do, let me go with adjacency dot add. So we have to add the different this one. What do we call? Edge actually. For that, I'll we went with a hash set, right? So I'll just go with a hash set here. And again, we have to go with the tree adjacency dot add. Again, the same thing, new hash set, and each node is its own root, right? So I'll just consider here parent of I. Let me assign this one to I, and finally rank of I. Let me assign this one to 0, not 1, 0. Yep. So this is fine. Let me come out of this one entirely. Let me format the code so that the code looks good. Now let's move on with the further things. I'll just go with a union find. So we have to find the root with a path compression, right? So I'll just go with a find here. Yep. So this one is X. Yep. This is fine. And if parent of X, if it is not equivalent to x actually, this part, parent of x, if it is not equivalent to x, then I'll just go with a parent of x. We are just going with a path compression here. If you know the DSU algorithm, so first we have to go with the path compression within the find, and then we have to go with a union. Within that will be going with a union by size or rank usually. Yep. So this is fine. So we have just went with a path compression here, and we have to return the parent. In simple terms, we are finding the parent here, right? So this is fine. Next, sorry. Next, what we are going to do here, int, okay, one, yeah. I'll just come out of this one entirely. Now, so this one will be completely, I have to remove this one. I'll just do one thing. So I'll just go with void union here. So I'll just consider int x as well as the y as variables. If you know the DSU algorithm, let's implement this one very quickly. I'll just go with rx equals here. So let me go with a find of x. Yep. And then let me go with the, sorry, let me go with the ry equals find of y. So I don't have to go with the find of y here for the this one ry. Instead, what I'll do, so yeah, let me go with the find of y. So as we are so this is perfect. So next, let me do one thing. If suppose rank of Rx, if it is equivalent to Ry, right? If it is equivalent to Ry, if both ranks are same, right? In that case, we do not have anything. We don't have to do anything. In that case, we just have to exit. I'll just give return. And one more thing here, if condition, if suppose R this one rank of Rx, suppose if it is less than rank of Ry, yeah, this part, then in that case, what we'll be doing, I'll just go with so let me assign T to Rx here. This is fine. And also Rx to this one Ry. So this is also fine. And finally Ry to the T. Ry to the T. Yep. So this is also fine. We are done with this part. So let me come out of this one entirely. Now, so let me assign, we have to attach the smaller rank tree under the larger tree, right? So for that, let me write it on this way. So that's the main thing we make use of the DSU basically, right? So I'll just go with the parent of Ry. Let me assign this one to Rx, and let me go with the if condition here. If rank of Rx, if rank of Rx equals again this one rank of Ry, yeah, rank of Ry. In that case, we have to increase the Rx. I'll just give here rank of Rx, not increase, increment basically. Yep. So this is fine. So this is it for the DSU. Let me format the code so that the code looks good. So I'll just come out of this one entirely. Now let's move on with the further things. So we are done with the what do we call find as well as the union. Next, we have to insert the edge. This one we have to insert the edge in the sense u to v, right? So for that, I'll just go with void insert. Yep. So let me go with two parameters edge u, but this one vertex u as well as the vertex v. We have to connect the edge, right? Or insert the edge, sorry. Yeah. For that, we need two vertex. So this is fine. I'll just go with a adjacency dot get here of u dot add of v. As we are dealing with the this one undirected graph, we have to go with the reverse as well. Yep. So let me copy the same thing here. Yep. Let me paste it over here. So in this case, I'll just go with a v. In this case, I'll just go with a yep. So this is fine. Now let's write the simple if condition. So if suppose if u and v in the different components, right? I'll just write see here. Suppose find of u actually if it is not equal to find of this one v. Suppose u and v are in different components. In that case, what we have to do, we have to merge the components. For merging, we have already written the union. So it will be union of u and v respectively. Next, after merging the components, the edge that we have considered becomes the tree edge. For that, I'll just go with the tree adjacency. We have already considered tree adjacency variable. I'll just go with dot get of u dot add v. Yep. Again, this one tree adjacency dot get of v dot add of u. So this one is fine as well. So finally, what I'll do, else non-tree edge stays in the adjacency list only. So we don't have to write anything for that. So let me come out of this one entirely. Now, yeah, let's move on with the delete operation. So it comes with insert as well as the delete. We are going with a simplified HDT actually. As I've said, so Euler tree will be going with the insert, will be performing insert as well as the delete operations as per the definition part. We had already discussed this one. Yep. Now let's move on with the delete. Yep. I'll just go with a void delete. So I'll just go with int u as well as the int v. Now within this particular method, I'll just go with the adjacency dot get u this one remove v. So this one same thing v dot remove of u as we are dealing with the undirected graph. Next, let's do one thing. So we have to check whether it is a true edge or not, or was it a tree edge? We have to check for that. So I'll just go with a boolean here. Boolean was tree equals tree this one adjacent we have to consider dot get of u uh, dot contains of v. Yep, so this is fine, it's simple. Yeah, we are just checking was it a tree edge. After that, when then we have to go with a non, if it is a non-tree edge, then the forest was unchanged actually. Forest has not changed anything, or forest is unchanged, then we are done with that particular part. So I'll just go with, sorry, I'll just write in this way, was tree actually. If not of was tree, then I'll just go with return. It's as simple as that. Now let's do one thing. We have to go with a tree edge that has been removed. Nothing but that is equivalent to the forest split, right? So if the edge we have removed, we had discussed this one in the approach, then we have to go with a forest split and search for the replacement edge. So I had shown you from 1 to 2 and 2 to 3, we had removed that particular edge and we considered the non-tree edge 1 to 3. That was shown in the dotted lines actually in the this one graph while we had discussed the approach. The same thing for that we have to write the code. How we can write the code? So I'll just go with tree adjacency here dot get of u remove of v. So this is fine. And again, the same thing, readjacency, get of v, remove of u. So this is fine. And we have to recompute the components from the scratch. Yeah. As we have completely deleted that particular edge and we had discussed the non-tree edge, we had rebuilt that one. We have to rebuild that one. We have discussed the non-tree. We have considered the non-tree edge, right? So we have to rebuild the graph actually. For that, we will be going with a rebuild union find. Let's do one thing. I'll just come out of this one entirely. First, let me make use of the this one, or let's go with the rebuild union find, and then we can just implement the same thing here, or we can just call that method here. So I'll just go with rebuild union find. So let me do one thing within this rebuild union find. So first let me go with a for loop here. This is fine. I'll just go with int I equals 0, I less than n. Let me go with I plus plus. So this is also fine. So let me go with parent of I. So this is fine. And rank of I equals 0. Yeah, this part. I'll just come out of this one. Next, let me go with a simple for loop. So I'll just go with int u equals 0, u less than n. Let me increment the u. Yeah, so again, I'll just go with one more for loop here. For so this one will be int. We have to let's consider the vertex v actually. Vertex v of 3 adjacency dot get of 3 u. Individual vertex we are considering from the u. So here I'll just call this one union of this one u and v respectively. So we are just rebuilding from the tree edges only. So that is the reason we are calling union here. So this is fine. I'll just come out of this one entirely. Now we have this one, right? So let's do one thing. So we have to get all the nodes before we get it to the main method actually. Let's do one thing. Yeah, so let's get all the nodes in the same component as start using the BFS on the tree edges actually. Yep, so for that I'll just go with set of integer So I'll just go with the get component here method. So I'll just go with a parameter start. So I'll give here int start. So this is fine. Within this particular method, I'll just go with a set. So let me go with integer. So this is fine. So let me go with visited. Yep, visited equals new hash set. Yeah. So visited dot add. So this one, let me remove this one. I'll just go with queue actually. Let me consider the queue. So this one will be queue of this one integer. So let me consider the linked list, or you can just go with the array dq as well. It doesn't matter, right? So before we have considered the hash set as well, right? So this is fine as well. No, so now let's add the start to the queue. So I'll just go with queue dot add of start. So this is fine. Then we have to add the start to visited. Once we have visited that particular vertex, so then we have to mark that one as visited, right? So I'll just go with visited dot add of start. So this is also fine. Then we are going with a pure DFS here. BFS, quite obviously, we have to go with a standardized BFS loop. Yeah, which consists of when queue is not empty. That part actually. Yeah, first step is so I'll just go with this one. The same thing. Instead of you, I'll just consider the variable. This one, what do we call current actually? Yeah. So this is fine. Int current equals q dot poll. So this is fine. Yep, it's as simple as that. Now let's move on with the for loop. So this one will be int nb. Yep, the new one we are considering. So I have named this one nb. So this one will be readjacency dot get of current. So why we have written in this way basically? So we have to walk only through the tree edges actually. For that reason, I have written in this way. Next, what shall I do? Let's write the simple if condition here. If visited dot contains rather than the contains, I'll just go with a add here, add of nb, the variable name that we have considered. So I'll just go with q dot add of nothing but nb itself. Yep. So this is fine. We are done with this part. Almost all we have to do is we have to return the visited. Yep. Let me do that. So let me format the code so that the code looks good. Now let's write the query, or yeah, let's write the query, or let's do one thing. We are done with this part, right? Which one? Get component actually. Get component basically. This one. Rebuild union find actually. Yep. Or one second. Where did I leave? I completely forgot. One second. Just give me a second. Yeah. We are going with the rebuild union. So we were writing within the delete, right? So I'll just do one thing. So we have to call this particular method rebuild union find whatever we have written. So let me, sorry, not this one. So let me copy this method and let me paste it over here. So I'll just call this method within the delete method. Now we have successfully called this one because we have to recompute the components from the scratch, because we have deleted that one, the edge, and we have considered the non-tree edge, right? So that is the reason we have to recompute the components from the scratch. So I have called the rebuild union find method here. Now let's do one thing. Let's go with the BFS from the use component to find the replacement non-edge tree. For that, let me go with a set actually, hash set or the set. I'll just go with set here of integer. Yeah, instead of this one, let me go with the name component u here. So this is fine. Yep. So let me go with, let me delete this one entirely. I'll just go with get component of u, get component of u. So this is fine as well. Now let's move on with a for loop. Within the for loop, let me go with individual node of this one. What do we call? Component u itself. Yep. So this is correct. Next, within this for loop, let's go with a one more for loop, nested for loop. So I'll just go with int neighbor of adjacency dot get of node. Yeah, we are considering the neighbor from the node itself, right? So this one basically we are checking all the adjacency edges. The second for loop I'm speaking of. Now let's write the simple if condition. So we have to check whether uh, whatever the crosses that we are considering, whether it crosses the cut or not. For that, let me write it in this way: if not of component u. this part actually dot contains of neighbor. Yeah, this one. Then suppose if we have found the replacement edge, in that case, let me call the union method. Yeah, union of what? Union of node as well as the neighbor. So I'll just go with the node and neighbor. Yep. So this is fine. This is correct. Then same thing. I'll just go with the tree adjacency dot get node of add neighbor. This is showing already. Yep. Again, dot get neighbor, as we are dealing with the undirected graph. The reverse edge also we have to consider. Dot get of neighbor dot add node. Finally, we have to stop actually. Yep. One replacement is enough, right? So here we completely removed 1 to 2, 2 to 3, that whole edge, and we did the replacement by considering the we replaced by considering the non-tree edge from 1 to 3 directly. Yeah, from 1 to 3 directly. So one replacement edge is enough. We have to stop there. For that, let me give the return. Yep. So we are done with this part. We are done with this part. So then one more thing. So no replacement is needed. When I say this part, so u and v are now in the different components. Now we do not need any replacement. So we do not have to return anything here. We don't have to return anything here. So let me format the code so that the code looks good. Now we are almost done with everything. We have written the rebuild union find as well. Now let's move on with the main part, nothing but the connected method. Yeah. So we need this particular method as well. So this is important. So I'll just go with this one is the small one. Don't worry. So I'll just go with Boolean. So let me go with the connected here. So I need two parameters. One is u and another one is v. Yep. So this is fine, I believe. So within the particular method, connected method, so I'll just leave here a return find of u, suppose if it is equivalent to the find of v. So why we are doing this one? So this one because for the path compression actually. So this will be because of amortized n, right? So because of amortized n after the path compression. For that, just for the optimization purpose, we'll be going with this particular one, right? So we are just checking query, are u and v connected here, right? So u edge, this one vertex u and v, whether it is connected or not, and this decreases the this one, what do we call, overall time complexity as well. So it will be because of this one amortized n almost, right? So it will be big of n, equivalent to big of n after the path compression. Now let's go with the main method. Yeah. So within the main method, we will be considering only the example, the same example that we have considered within the when we had discussed the this one algorithm or the approach. So I'll just copy paste the same thing. Just give me a second here. So let's do one thing. I'll just paste this one over here. See, we have considered the same example actually. So this one will be not HTT. So the same thing. Yep. Let me format the code 1 second. Yeah. So here, so I have just called the main method here, main function. So we are going with the 4 nodes actually here, right? So this is the main class name. Sorry. So we are going with the 4. This one. What do we call? 4 nodes here. You can clearly check. So we went with 1 to 2, 2 to 3, and 3 to 4. So we have successfully written the insert as well as another method is delete. As per the definition, so we went with a simplified HTT. So there we are considering only two methods. One is insert and another one is delete. Yeah. So within the insert, what we are doing, as we are going with the 4 methods, so we are going with the same example. If you remember, 0 to 1, 1 to 2, 2 to 3, and 0 to 2. So we are just going with a zero-based indexing. Well, I showed the graph actually. We went with a 1 actually, 1 to 2, 2 to 3, 3 to 4. Instead of that, we are going with 0 to 1, 1 to 2, 2 to 3, as well as the 0 to 2. Yep. So then what we are doing here, so this one we are just printing whether 0 to 3 is connected. 0 to 3 will be connected accordingly with what we had discussed actually. It will be 0 to 2 and 2 to 3, right? 0 to 3 has to get this one has to be connected. Here we have to get the boolean value true, right? So this is fine. Next, g dot delete, what we are doing, we are removing the tree edges and then we are searching for the replacement here. This one we are removing. What we are removing actually, we are removing the tree edge and we are searching for the replacement. In this case, 0 to 3, 0 to 2 replaces 0 to 1 and 0 to 2. 0 to 1 and 0 to 2, as I had shown you in the approach or the algorithm part, while we considered the same example, but we started from 1 to 2, 2 to 3, 3 to 4, right? So 1 to 2, 2 to 3, that edge was deleted actually, and we considered 1 to 3 directly, non-tree edge. Here as we are starting from the 0 to 1, 1 to 2 basically will be deleted, and we will be considering the non-tree at 0 to 2 directly. That's what we'll be doing. Yes, so we will be finding the replacement. So in this case also we have to get the Boolean value true. Yep. Finally, we are just removing the 0 to 2. 0 to 2 edge itself we are removing. Then we are checking whether it is connected or not. So if we remove the 0 to 2 itself, we do not how for this one, how the graph will get connected actually, how the edges get connected actually. 0 to 1, 1 to 2, there is no connection at all. 0 to 3, there will be no connection, quite obviously. Only we'll be having the connection from 2 to 3. From 0 to 1 and 1 to 2 will not be having any connections. At least we should have direct connection from 0 to this one, what we call 0 to 2. We do not have any connections when we remove 0 to 2. So in that case, for the third one, we have to get the Boolean value false. Yep, it's as simple as that. If you understand the algorithm implementation or the example part, you will that's a piece of cake. Yeah, you'll understand this one very fast actually. I can assure you that. And one more thing, if you understand the whole algorithm, implementing the same thing while solving the problem will be very much easier, right? You can just make the templates. Yeah, while you're solving the problems, make certain templates, and you can just make the changes. You can just if you are solving some problem, you can just paste the template and make the necessary changes. That also you can do. Yeah, so that is the reason you have to understand the algorithm part, this one clearly, so that the further implementation becomes easier, right? So we are done with this part. We are done with the algorithm part actually. So let's do one thing. Let's run the code that we have written. So let me format the code once so that the code looks good. Now I'll just come here. Let me run the code. We are getting 0 to 3 false. We are checking only for the 0 to 3. Why? What's wrong here? One second. So let's do one thing. Let me minimize this one. Let's check the path compression as well as the this one. Delete is fine. Now this is fine. Where did I write the DSU part one? This is the union part. Yeah. Oh, here see. We don't have to check for the rank actually. Just have to check whether this one Rx is equivalent to Ry or not. The value actually. So let me format the code. Now, if I run the code, then we have to get the correct output. Yeah. So connected 0 to 3, true. For the first one, we are getting true. For initially, it is connected from 0 to 1. So I'll just show you this one directly over here. One second. Mm, so graph is initially it will be, I have already shown you this one during the example actually. Let me show you this one very quickly. So this one will be 0 to 1, 1 to 2, and 2 to 3. Initially this will be connected, so we are getting the output true. Then the second one, 0 to 3 is connected again. So this one we have given within the S out after removing the this edge. So initial graph is this one. Yeah, initial graph is this one. So we have two ways actually: 0 to 1, 1 to 2, and then 2 to 3, or 0 to 2, 2 to 3. So here we will be deleting 1 to 2, this edge actually. So this edge doesn't work as well. So we will be checking for the replacement. The replacement is from 0 to 2. We have this one directly actually. Now this becomes 0 to 1, 2. So 0 to 2 we have the replacement edge actually. Yeah. Then 2 to 3 we have the edge. So here 0 to 3 is still connected. Yes, after the removal of 0 to this one, what do we call this edge, 0 to 1 and 1 to 2, basically after deleting the 1 to 2 edge, we still have the connection. So this one also we have to get true. We are getting the output true, which is absolutely correct. Then for the third one, connected 0 to 3 false, because we have given S out, or we have made use of the system out println after removing the this edge 0 to edge itself. Now we have 0, 1, 2 and 2 to 3. We do not have any edge from 0 to 1, 1 to 2. This one we do not have any edge at all here. So it 0 to 3 is still connected. No, it is not connected. In that case, we have to get Boolean value false, which we are getting actually, which is absolutely correct. Which is absolutely correct here in our case. So whatever the code that we have written, we are getting the desired output. So we have considered the example in this particular way. So whatever the code that we have written works absolutely correct, and we are getting the desired output. Yeah. So let me delete this one. Where is this one? Yeah, let me delete this one. So this is fine. So let me minimize this one. So this is fine. We are done with the this one, Holm-de-Lichtenberg-Thorup algorithm, right? So this is mainly also, this is used for the dynamic connectivity in a graph. Yep. So we are done with this part. Next, let's do one thing. Yeah, let's try to implement the same thing in the this one within certain problem. Yeah, let's consider some problem and let's try to implement the same entire algorithm within the this one. Yeah, within the problem that we consider. Let's do that. So let's move on with the problem part here. So you can clearly see here, Dynacon 1 dynamic tree connectivity. So this is one of the best problems I have found to this one implement the complete Holm-de-Lichtenberg-Thorup algorithm. Yep. So let's see what the question states here. You can just go through the question. It's very easy to understand. Yeah. The question is not that much difficult to understand, but implementing the algo might be, so if you don't know the algorithm correctly, it might become a bit difficult. But this question, whatever however they have given the question, they have given in a very good way, and understanding the question plays a prominent role. Yeah, first you have to understand the question correctly. So I can just go through the question. Yep, they have clearly mentioned the input output part as well. I'll just summarize the question so that we understand the question even better. It will be easier for us to solve the problem. Just give me a second here. 1 second. Yeah, so first thing here. Yeah. First thing, so we have to maintain a dynamic forest. Yeah, that's what they have asked in the question. We have to maintain dynamic forest of n vertices. Yeah, of what? Of n vertices. Yeah, I'll just write here n vertex. For the vertex, I'll just write VTX here. Right. So we have to maintain a dynamic forest of n vertices supporting three operations. Yeah, it supports three operations. What are the three operations? The first one is we should be able to add the edge. Yeah, first one, we should be able to add the edge. Second one, so this is guaranteed actually, no prior path exists, so we should be able to add the edge. Second one is remove the edge. Yeah, so accordingly with the algo, so if you remember correctly, in the algo we went with a simplified this one Lichtenberg-Thorup algorithm, where we went with add as well as the remove operations itself. Yeah, within the algo. Yeah, so we should be able to add, we should be able to remove, and the third one is nothing but we should be able to query as well. Yeah, we should be able to query as well. So I'll just write here QUE or QRY. So let me write here QRY, nothing but the query. So again, so we have to maintain the dynamic forest of n vertices supporting three operations. One is we should be able to add an edge, and we should be able to remove an edge. Sorry, we should be able to remove an edge. And the third one is nothing but we should be able to query the connectivity between the two vertices. Yeah, we should be able to query the connectivity between the what? Two edges. So let me write it over here. We should be able to query the connectivity between the two edges. Yeah, these three operations we should be able to do. Okay, very simple. Now, so we have to output yes or no for each connection query. So after querying actually, if it is possible to this one, what do we call? If it is possible for the connection, then we have to output yes in that case. If it is not possible, in that case, we have to output no. So these two things we have to keep in mind. Yeah. Again, so we should be able to output yes or no for each connection query. So yep, as I've said, if the connection is possible, in that case we have to output yes. If the connection is not possible, in that case we have to output no. Yeah, so this is fine, I believe. This is it for the question. So let me read this one out loud again. Just listen to this carefully. We have to maintain the dynamic forest of n vertex. Yeah, we have to maintain the dynamic forest of n vertices. So supporting three operations. So one is add, another one is remove or delete, third one is query. Right. So query nothing but query connectivity between the, we have to query the connectivity between the two vertices. We have to output either yes or no. Right. So if the connectivity is possible, then we have to output yes. If no, then we have to output this one no here. So that's what they have asked, right? For each connection query, for the each connection query, we have to either output yes or no. That's what they have asked in the question. So this is it for the question. It's as simple as that. Yep. So now let me delete this one. Yep. So this is fine. Now let's do one thing. As we have complete understanding of the question, let's do one thing. Let's discuss the approach. if everything goes well, after discussing the approach, let's try to articulate the same thing, whatever we had discussed in the form of code. So if everything goes well and if we get the desired output, then we can just move on with the complexities part. First, let's do one thing. Let's discuss the approach first. Yeah, let's do that. So let's do one thing. Let's move on with the this one approach part actually. First thing, the algorithm uses Holm-de-Lichtenberg-Thorup dynamic connectivity with a log leveled ETT. ETT nothing but Euler tree tour actually. Yeah, this one ETT part that I'm speaking of. One second. Yeah. Again, the algorithm uses HDT, nothing but Holm-de-Lichtenberg-Thorup algorithm. Lichtenberg-Thorup dynamic connectivity with a log leveled ETT, nothing but the E stands for the Euler, T double T stands for tour tree actually, tree tour actually. Anyways, now let's move on with the further things. Each edge gets a level. Accordingly, with the algorithm, we have already discussed this one. Each edge gets a this one level. So 0 to logarithmic n. We have already discussed during the algorithm part. Now tree edges maintain the spanning forest. We know this one from the algorithm as well. Tree edges maintain the this one spanning forest. Non-tree edges nothing but we call it as NTE. Non-tree edges in our case within the algorithm, the non-tree was 1 to 3 if you remember correctly. Yeah, non-tree edges NTE are the extras actually. Yeah, so we had considered 1 to 2, 2 to 3, 3 to 4, 4 to 5, right? 1 to 3 was the extra actually, it was the non-tree edge. So non-tree edges NT are the extras. On deletion of the tree edge, we search for the replacement. Yeah, on deletion of the tree edge, according to the input they have given, on deletion of the tree edge, so we have to search for the replacement edge among the non-tree edges. We have to search among the non-tree edges itself. They have strictly mentioned, the algorithm also states that itself. Yeah, we have to always search for the replacement among the non-tree edges itself. Yeah, this is fine. We search for the replacement edge among entities at the same level. At the same level, right? If we are considering at the level 0, we'll be checking this one for the replacement among entities at the same level, promoting the edges. This one, promoting the edges upward if needed. So promoting the edges upward if needed. So we have already discussed this one. I just wanted to brush up actually the algorithmic part. So we have brushed up. Now let's move on with the further things. So let's consider the same example. Let's consider the same example that they have given in the question. So this example you can clearly see here. Look at the left side where I have this one, where I'm showing the pointer actually, where I have kept the pointer or the mouse. 5, 11. So we have been given connection 1, 5, add 1, 2, add 1, 3, add 3, 4, add 5, 4, connection 1, 5, remove 4, 5. Connection is for the to check actually query. Connection is nothing but the query, add is nothing but the insertion, and rem is nothing but the remove. These three things itself we have to maintain accordingly with the question. Connection of 1, 5. So 5, first 5, 11, what it indicates, let me tell you. 5 is nothing but the number of vertices within the graph, and 11 is nothing but the number of edges. So these are the edges they have given. You can count actually, you will get 11 edges. Yeah, connection, we have to check for the query 1 to 5. We have to insert 1, 2. We have to insert 1, 3. We have to insert 3, 4. We have to insert 5, 4. Yeah, then again we have to query for the 1, 5. We have to remove 4, 5. We have to again query for 1, 5. We have to remove 3, 4. We have to insert 3, 5 or add 3, 5. Finally, again, we have to query for 1, 5. So this is the input they have given, and the output that we need to get is no, S, no, as well as S, right? So this is fine, I believe. So this is it for the input output part. So let's consider this entire input, right? So graph initially, vertices they have given, see here, you can clearly see the vertices they have clearly mentioned 5, and edges they have clearly mentioned 11. Vertices is from, will be starting from the 1, so 1 to 5 will be considering. So initially graph, so this is the graph actually, 1, 2, 3, 4, 5, all are isolated here, right? All are isolated. First what we'll do before querying, so forget about the query part. First we have to add 1, 2. Let's go with the insertion part. We have to add 1, 2. So we have successfully added 1, 2. So this is the first part. We have successfully added edge 1, 2. Yep. Then again, let's search for the add. Add, we have 1, 3. So we have added this one vertex 3 from 1 actually. Yeah. This is all. This also becomes one path. 1, 2 was already there. Then now we have 1, 3 as well. One second. Yep. Now we have 1, 3 as well. Yep. Next, let's move on with the third. You can clearly see here after 1, 3, we have to add 3, 4. Yeah, we have to add 3, 4. So let's add 3, 4 here. We have 1 2 1 3 already, and we have successfully added 3 4 to the graph. We have successfully added the edge 3 4 to the graph. Next, here you can clearly see we have to add 5 4. Yeah, we have to add 5 4. You can clearly see here this part we have to add 5 4. Yeah, so 1 2 we already have, 1 3 we already have, 3 4 also we already have. This one we have added this time. Yeah, this one we have added this time, nothing but 4 5. Yep, or 5 4. They have given 5 4 or 4 5. It is undirected graph, so we can consider the reverse edge as well, right? Reverse part. So this is fine. Next, we have to query this one 1 5. This one. Let's this one. Let's ignore the query part. Then we have to remove 4 5. So currently we are not into, yeah. We have to remove 3 4, or 1 second. We have to remove 3 4 they have given. Yeah. So here let's look at the removal part. Actually, first they have given here this one, removing the 5 4. Where is 5 4 actually? Yeah, remove 4 5. Before removing 4 5, let's consider this one. It can be of any order basically. First let's remove the 3 4. This they have given actually, remove 3 4. So first when we remove this one 3 4, or let's consider 4 5 itself, this part itself, as I've written the graph in the order itself. Let's consider this part itself. We have to remove for the 4 5. So we have successfully added 5. So now the graph looks like this actually. Yeah, 1 2 3 4 5. We have 5 vertices. Basically the graph looks like this. Yeah, now let's come to the removal part. First removal in the input they have given 4 5. Yeah, you can clearly see here rem of 4 5, nothing but removal or the deletion. 4 5, when we remove 4 5, so this one, see, 5 splits off here, 5 splits off. So we have removed this edge. Yeah, we have removed this edge actually. Yeah, we have successfully removed this edge. So 5 splits off. Then we have the second removal here. After removal, we have second removal 3 4. You can clearly see here this one where I have pointed, removal of 3 4, edge 3 4. Now we have removed this part as well. Next we are removing this part. Now see, 4 splits off actually. 4 splits off. We have in this way the graph now. 1 to 2 is connected, 1 to 3 is connected. 4 and 5 have split their way, right? Split their way in a different direction actually. 1 to 3, 1 to 2 they are connected, 1 to 2 they are connected, 1 to 3 they are connected. So now 4 and 5 are split actually, they have split. Now this is fine. Next we have to add 3 5. We have to add 3 5. So removal part is done actually. We have only 2 removals in the input. After this one 2 removals in the input, they have again asked us to add 3 5 actually. Yeah, they have again asked us to add 3 5. So we will be adding this part. This time 4 will be split still. 4 will be split still, but 5 we will be connecting. 5 we will be connecting to the 3, as they have given in the input that we have to connect for the 3 5. We will be connecting this one. Yeah, we will be connecting this one. Now we have this particular graph actually. This is the final graph that we have got. Yep, final graph that we have got. So now we have performed add as well as the this one, what do we call, remove operation. So still we have to query 1 5, query 1 5 we have been given twice actually here. That's it. Query 1 5, query 1 5 as well as query 1 5. We have to query 1 5 itself, right? So this is fine. 1 to 5 they have given. So after the removal, after this one, we have to do. So for the first one actually, for the first one we have got this one no, we have to get no. For the second one we have to get yes. For the third one we have to get no. For the fourth one we have to get yes. So this one is the first input, connection 1 to 5, this one until adding 5 to 4. Then one connection 1 to 5 until this one, what do we call, removing 4 to 5. Then the third input is connection 1 to 5 until adding 3 to 5. The fourth one is nothing but connection 1 to 5. Again, finally we have to just query 1 to 5 again. So the output no yes, no yes we have to get. So let's move on with a step-by-step explanation here. For the connection 1 5, so first query that we are considering here, right? For the connection 1 5, no edges. Still we do not have edges yet. Yeah, we still just have the vertices 1 2 3 4 5. No edges are connected yet. We do not have any edges initially, so all are isolated. In this case we have to display no. We will be getting the output no. So that's what we have got here in the output section. You can clearly see. Now it is clear how we got no first output. Yep, so this is simple. For the second one, we are adding 1 to 2, 1 to 3, 3 to 4, 3 to 4. Yep. And adding 5 to 4 as well, these things, right? So this builds the chain 1 to 2. This is the final one, right? So the second step I've already shown you, this one actually, until this one, successfully adding. So I'll just consider the graph, the last graph itself, 1 to 2, 1 to 3, 3 to 4, and 5 to 4. This builds the chain 1 2. So this builds the chain 1 2 and 1 3 4 5 actually, 1 3 4 5. Actually, this is not the second one actually. Where did it go? This main graph actually. Everything is connected. So 1 2, this builds the chain, and then 1 3 4 5. This part actually becomes this one. What do we call connected? Right. So this part becomes connected. So it builds the chain 1 2 1 3 4 5. I have clearly shown you the graph. You can just pause the video there and you can just look that part of the graph actually. Now we have again. So we have got no for this, right? So now we have to query 1 to 5 again, this part. Yeah, this one, where is this? Yeah, this one, we have to query 1 to 5 again. So we'll go with the connection 1 to 5. Now we have the path 1 to 3, 3 to 4, and 4 to 5 exists. In that case we have to display yes, we have the path, right? So when we have the path, we have to this one, display yes, right? Output is actually, yeah, we have successfully displayed the output is here, right? So first one no, second one is so the same output they have given here, the s actually, right? So this is fine, I believe. Next, let's move on with the removal part actually. Now we have a removal. See here, connection 1 5, removal of 4 5, and this one, removal of 4 5, this one. Yeah, let's move on with the what do we say? Removal of 4 5. So here we will be removing only bridge between 1 2 3 4 and 5. Yeah, 1 2 3 4 and 5. So we have to remove 4 to 5, right? So where did it go here? This part we will be removing actually. So the graph looks this one. This one we will be considering this graph actually. Yeah. For that reason itself, I have drawn the graph actually step by step. So now we have removed this part. Removed this part means 5 splits off here, right? 5 splits off here. So as 5 splits off, so no replacement is found. Yeah, no replacement, meaning non-tree edge is not found. We do not have any non-tree edge here to connect this one 4 to 5 or 5 to 4. We do not have non-tree edge, so no replacement found. So for 1 to 5, no replacement is found for 1 to 5. So again they have given connection 1 to 5, we have to query for that. So as no replacement is found, we will query for 1 to 5. So we can query until 1 to 4 only. So we do not have replacement, non-tree replacement edge, non-tree edge actually. So we cannot connect from 4 to 5. So this is not possible. We are not able to connect from 1 to 5 as we are querying from 1 to 5. In that case, we are displaying no, output no. For the third one, we have got the output no. See here, the same output here they have shown. Yeah, we now know that how we got no, yes, no, and finally we have to start from here actually. Removal 3 to 4. So let's move on with the same thing. Removal of 3 to 4. 3 to 4, let's go with this part actually. Now we have 4 to 5 is split, and now we are splitting this part as well. Yeah, now we're splitting this part as well. 3 to 4 we have uh, this one, we are removing this particular edge, so 4 completely splits off as well. Similar to the 5, 4 completely splits off as well. Yeah, so now 4 is now completely isolated. Yep. Next, we have asked to add this one, edge 3 5. The last step, we have successfully added the 3 5. Now we have the connection from 1 to 2, 3 to 4, 3 to 5 actually, 1 to 2, 3 to 5. Now we have the this one, non-tree edge, right? From 1 to 2, 4 is still isolated, no doubt, but 3 to 5 there is a connection. We have to see whether we have from 1 to 5, right? So 1 to 2, then we have this one. Basically, yeah, 1 to 2, we have 1 to 3 as well as 3 to 5. Basically, from 2 1 3 5, we have the edge from 2 1 3 5, right? So we can still, yes. So in that case, what we will do, 3 connects to 5. Path that is found is nothing but 1 3 5, right? 1 3 5 actually, this path, as I mentioned, 2 1 3 5. So basically, we'll check from here. From 1 to 5, we are checking. So this one will be 1 to 3, 3 to 5. Yep. 1 to 3, 3 to 5. So the path exists here. 1 to 3, 3 to 5. So the connection again we have to query. So this is for 1 to 5 actually. The path would be 135 and the path is possible and the path exists, so we have to display yes. In that case we have to display yes. So that's what they have given here. So we have got the output s. So this is how we got no s, no as well as the s accordingly with accordingly by applying the this one, what do we call, um, Lichtenberg-Thorup algorithm. So we have got the correct output accordingly what accordingly with what we have discussed just now, right? By considering the input or the example input itself they have given in the question. So now this part of the problem is completely clear. Now let's do one thing. We are done with the problem part. Yeah, we are done with the complete problem part. Now we complete have the idea on the problem as well. We have the complete idea on the problem. So let's do one thing. Let's try to articulate the same thing in the form of code. We will be making use of complete Lichtenberg-Thorup algorithm. We'll be implementing the same. Just listen to this carefully. We'll be implementing entirely because we had considered only insertion and removal when it came to algorithm, right? So we went with a simplified version. We made use of the Euler two tree no doubt, but we didn't make use of the query actually, or we went with a connected, yeah, we went with a method called connected, but still we went with a simplified version. There are certain things we removed accordingly with the theory. We considered actually there are certain things missed. We will be implementing the entire algorithm for this particular problem. Even for the optimization purpose, we have to use the complete Lichtenberg, this one, what do we call, a Lichtenberg-Thorup algorithm. We will be tweaking a bit because the algorithm would lead to, if we implement the entire algorithm, the time complexity would lead to big of log square n. So instead of that, we will be accordingly with the constraints they have given. Let's go with a big of n log n, because see, at the end the constraints will not pass. We will be making a bit of this one, what do we call, we will be tweaking a bit actually within the connected this one method. Let's see that one in the future. For now, all we have to do is we have to articulate whatever we have discussed in the approach. Let's articulate the same thing in the form of code by making use of the Java programming language. Let's do that. Let's do that quickly. Let's do one thing. Let's start writing the code. I'll just come here. Let's open the IntelliJ. So let me open this one. Uh, mm, Dynacon, dynamic tree connectivity, the problem in the SPOJ, right? SPO online checks actually. Yep. Let's do one thing. I'll be making use of the this one buffer data and the print writer. So let me import input output package. So I'll just go with java.io.star and let me import this one utility package as well. So this one, this is fine. So next what I'll do, let's do one thing. Let me go with certain global variables here. I'll just go with static final. Yeah, let me go with final int maxn equals, I'll just go with 100,005. Yeah, this is fine. The next part is nothing but static here. Final. Yeah, I'll just go with final int. Let me go with max log. So let me consider this one 17. Yeah, what are these two things actually? So we need the maximum number of vertices. So I have considered max and here nothing but max nodes or max vertices. Yeah. So this n nothing but the maximum nodes. So the value is this one. So and this one max log is nothing but log 2 to this particular value. Basically it's 1 lakh, right? So log 2 of 1 lakh. So it is almost equivalent to the 17 levels for the this one Holm-de-Lichtenberg Thorup actually. Yep. So this is fine. Next, let's go with a tree actually. This is what I said. We didn't go with a tree when it comes to this one algorithm. We'll be making use of the tree. Actually, pure HDT involves the tree. For the tree, we'll be going with the implicit tree that is equivalent to the Euler two tree, right? So let's consider the node arrays actually. Let's do one thing. Let me go with static here. Let me go with int. So this is fine. I'll just go with the variables TL. Let me go with the variable TR, as well as for the parent, I'll just go with a TPAR. So this is fine. We have successfully considered left child, right child, as well as the parent pointers. Next, we'll be going with subtree size random priority as well. Nothing but it is one of the heap property. So as we are going with a tree, nothing but tree plus heap, right? So I'll just go with static. Let me go with int here again. So I'll just go with tsc, nothing but the subtree. This one, what do we call? Subtree size SZ is nothing but the size, subtree size, and we have to go with the priority as well, right? So I'll just go with the T PRI, nothing but the priority. So these two things are fine. Next, let's move on with the this one. So I'll just go with this one more variable, two more variables actually, or let me go with the three. So NT is nothing but the this one. What do we call? Non-tree edge actually. Yeah. Then I'll just go with a n this one. What do we call? T and T on on is nothing but, suppose we'll be checking this one. This vertex owns an NTE at this particular level. For that, I'll be going with a T on, as well as one more variable, nothing but TVT, nothing but T vertex. Will by making use of this variable, we'll be checking, is this node a vertex node, right? If it is, then we'll be displaying true, or edge node. Then we'll be displaying actually false. So I'll just consider these three, this one, what do we call, nodes. I'll just go with static here. So this one will be Boolean. So let me go with T and T. So this one I'll just go with T and T here. Non-tree edge actually. Then I'll just go with a T on. We have already discussed this one, and T vertex actually. Yep. So this is fine. So after this part, let me do one thing. Let me go with the NC. So let's go with a node counter. Node counter, nothing but the allocator actually. Yep, I'll just go with a static int node counter. Let me initialize this one with a 0. Then one more thing we need fixed seed for the this one, reproducibility. Reproducibility in the sense, see, so when we remove the edge, and when we consider if there is a replacement found, actually we have to consider that particular edge. Yeah, we have to consider the we will be searching for the non-tree edge, and if we have found that one, again we have to build the tree, and again we have to reproduce whatever this one, whatever we have. If we have to check whether the edge, or we have to query, suppose accordingly with the input, the edge is present from that particular edge to the last edge, that we have to check, right? So for the reproduce this one, for the fixed seed for reproducibility, I'll be making use of, so let's go with final here. So this one will be random. Yep. I'll just go with RNG here, equals new random of, let me pass here the value 0 x de. I'll just go with a deadbeef here, right? So this is fine, I believe. Next, let's do one thing. So after this, let's move on with a node allocation. Yeah, let's move on with a node allocation. So I'll just go with a static int. So let me go with new node here. So this is fine. So next, what shall I do? Let me go with a Boolean. This one, what we call is vertex parameter. 1 second. Yeah, I'll just go with new node. So let me go with Boolean here, is vertex. So this is fine. So let's move on with the further things. Now let's allocate the next slot. For that, I'll just go with x equals. Let me increment this one. Yeah, new counter, right? Sorry, node counter. So so we have allocated the next slot. So suppose if no children and no parent, in that case, let's do one thing. I'll just assign TL of x, so not YL, we have considered TL, right? So this is fine. Let me assign this one to TR of x. Yeah, and also parent. Suppose if they are not having parent as well as no children as well, right? So I'll just go with a TPR itself we have considered, right? Let's initialize all this one to the 0. Why we are getting this one now? TL of x, this is fine. Equals TR of x is also fine. Equals T parent of, oh, I have not mentioned x here. That is the reason they're showing error. Anyways, now the error should be gone. Yeah, this is fine. Now let's consider size equals 1, right? Initially, let's consider size equals 1. So I'll just go with the size. So the size of x, or else we'll be getting the error. So let me assign this one to the 1. This is fine. Now let me go with the T priority as well. So I'll just go with T pre here of x. Don't forget x. Yeah. So I'll just go with a RNG. Yep, RNG dot. Let's make use of the next int here, right? So this is fine. We are done with this part. Again, I'll just go with a TNT. Yep. So of X. So I'll just go with this one. T on this part, and let me assign this one. Let me assign this one to the boolean value false. Now we have to mark whether vertex or edge node. For that, I'll just consider the vertex of X. I'll just go with this one. Let me assign this one to is vertex. Yep. So this is fine, and we are left with only one thing, nothing but 1 second. We have to return X. All we have to do is we have to return X. Yep. So this is fine. Let me format the code so that the code looks good. Now let me come out of this one entirely. So we have to pull in the sense we have to aggregate up, right? So within the pull method, we will recompute the size and NT flag, nothing but non-tree edge flag from the children, right? It must be called after any structural change. So let's move on with the pull method. So I'll just go with the static here, void. So let me go with the pull. I need parameter X. Yeah. So suppose if the value X equals 0, in that case we have to stop. I'll just give a return. So let me go with the t size here. T size of X, yeah, equals t size of this one. I'll just go with here TL, yeah, TL of X plus 1. So this is fine. And also let me go with plus t size of so let me copy the same thing here and we paste it over here. Instead of the L left, I'll just go with the right here, right? So this is fine, I believe. Yeah, this part is completely clear, I believe. Next, what I'll do, all we have to do is if the NT or the non-tree edge exists anywhere in the subtree, we have to check for that. Suppose if the non-tree edge exists or not. For that, I'll just go with the TNT, this one, non-tree edge of X actually. X, we have to go with a small x, right? So I'll just give here T on this part on of X. Again, logical or I'll just go with a T non-tree edge. Again, this part of X. Let me go with a T left of X actually. Yeah, this is fine. Or so let me go with TNT. This one. What do we call? TR. Nothing but the right. Yep. So this is fine, I believe. We are done with this particular method. So let me come out of this one entirely. I'll just come out of this one entirely. Now let's do one thing. We have to split by position. When I say we have to split by position, basically we are splitting the tree that is rooted at X into 0 to K minus 1, right? 0 to K minus 1 into split L and K to N minus 1 into split R for the left and right side. So how can we write that one in the form of code? So I'll just go with certain variables first. So let me go with, sorry, what did I write here? 1 second. Yeah, I'll just go with a static int. Let me go with a split left as well as split right. Yep. So this is fine, I believe. Next, let me go with a split case. So I'll just go with static void split k. Yep. So let me go with two parameters. One is x and another one is k. Yeah. So within this one, within the method split k, let me remove this one. First thing, let's do one thing. We have to check for the empty tree. Suppose if the tree is empty, so I'll just go with if x is equal to 0, then in that case, what we'll be doing, I'll just go with split L equals both split R. So this one equals 0. Yeah, and we have to stop so that I'll just give your return. Yep, so this is fine. Let me come out of this one entirely if condition. So we have to go with the number of nodes in the left subtree. For that, I'll just go with the int ls. So I'll just go with t size of t l of x actually, this part of x. Yep, so this is also fine. 1 second. mm, the next step would be suppose k falls in the left subtree, then we have to split the left subtree. Suppose k falls in the right subtree, then we have to split the right subtree at the adjacent index. These two things we have to write the if condition for these two conditions. So I'll just go with if lx, if it is greater than or equal to k, in that case I'll just go with split. So we have to go with a split k, right? Yeah. Let's recast actually. Split k of TL of x and x comma k actually. Yeah, this is fine, I believe. Next, I'll just go with TL of x here. Yep, let me assign this one to the split right actually. So let me remove this one. I'll just go with split right. This is also fine. Then let me write one more if condition here. If split r right side actually, if it is not equal to 0, in that case what we have to do, I'll just go with a t parent. So let me go with split r. Let me go with split right or the split r. So let me assign this one to the x. Now t parent, so this one of x, let me assign this one to 0 and let me go with a full of x. Yep, so this is also fine. Finally, split r. So this one, let me assign this one to the variable x. Right. So I'll just give else here. So within the else, let me do one thing. If the k falls in the right subtree, then we have to split the right subtree at the adjusted index. For that, I'll just go with a split x, or let me go with a split k here. Split k of dr of x. This time I'll just go with the right side, dr of x as well as the this time it would be k minus ls minus 1. Yep, or hyphen 1. So I'll just go with the tr of x here. Let me assign this one to the split left, not the right. Now let me write the simple if condition here. If split r, if it is not equal to 0, then t parent of split this one. Here I have to change this one to L. So this one will be equivalent to x and t parent of this one x. So let me assign this one to the of x equals 0. Yeah, let me assign this one to the 0 and let me go with the, so I'll just write this one, put this one in the next line actually, so that this looks good. So I'll just go with pull of what, pull of x, right? So this is fine. And split let's this one assign this one to the x. So this is it for this particular condition. This is it. So let me come out of this one entirely. So this is it for the method as well. This particular method, split k method. Yeah, so let me format the code so that the code looks good. I'll just come out of this method entirely. Now let's move on with the next method. So we have to split before a specific node. Yeah, I have shown you the step by step, the split part actually. So example, we have 5 got split first, then the 4 got split. Yeah, we have to split before a specific node. So basically let's go with a split before method here. I'll just go with static here. Let me go with void. I'll just go with split before. So let me go with a parameter v. So within this particular method, first thing I'll just go with the position equals t size. Where is size actually? This one. T size of t left. Yep, t left of v. Right. So this is fine. Next, let's consider the current value. I'll just go with the current here. Let me assign this one to the vertex v. Yeah. So first 2 lines, nothing but we are considering the node to the left within the v subtree. Then we have to write the while condition because we can walk up to the root accumulating the particular position. So I'll just go with while here. While t parent actually, let's consider the parent here. T parent of current actually, not the position. Current, if it is not equal to 0, in that case, what we'll do, I'll just assign the variable p to t parent of current. So this is fine. And then let's write the simple if condition. If t right side, if tr of p, so suppose if this is equal to current, yeah, if this is equal to current, then position equals position plus, I'll just go with a t size here. TL of B, TL of B. So this is fine. TL of B plus 1. Yeah, plus 1. Now this is fine, I believe. Error will be gone. Yeah, this is fine. Why we have written this if condition here? We are just adding the left sibling plus also the parent actually. Yeah, if coming from the right. So that's what we have done. So finally, let me assign the current to P. So this is fine. And let me come out of this while loop and let me give split K. So let's make use of the split K method which we have already written, and let's pass the parameters current as well as the position. So we are done with this part. Let me format the code, and we are done with this part. Yep. So this is fine. Yeah, we are done with the split before method. So this is fine, I believe. Now let's do one thing. We have to merge the two trips. As we are going with the trips actually, we have to merge the two trips. After the removal, we have to merge again, right? If we have found the this one, what we call non-tree edge, then we have to merge. For merging, so I'll just go with static here. Int, let me go with a merge. So I'll just go with int a comma int b here. So this is also fine. So first condition, suppose if a equals 0, in that case, within the if condition, if b not equal to 0, then I'll set the t parent, this one parent of b. Let me assign this one to 0, and I'll just do one thing. Yeah, let me return b here. So this is fine. So let me come out of this one entirely. Let me copy the same thing again here and make the necessary changes when b is 0. Yeah. So when b equals 0, in that case, if I'll just go with, instead of the if condition, let me directly go with, no need of if condition here. So what happened to this one? Oh, sorry. I'll just remove this one. This is not required. So I'll just go with a t parent of, instead of b, I'll just go with the a here. So let me assign this one to the 0, and let's return a instead of b. So this is it for if condition actually. Yeah, we have written two if conditions. So I'll just come out of this if condition as well. Now let me assign the variable r. Let's move on with the further things. So we have to check whether a has the higher priority. If A is having the higher priority, in that case, A becomes root. Yeah. Then we have to merge the right subtree of A with the B. Suppose if B is having the higher priority, then B becomes the root, and then we have to merge the left subtree of this one, A with B. So that's what we have to do. These two conditions. Again, let me write the simple if condition here. If T, let's go with the priority, as we're dealing with the priority. So I'll just go with the PRI here, this one, T pre of priority. If A is greater than, let me remove this one, less than. If it is greater than B, yeah, in that case, what we have to do, I'll just go with the TR of A. Yeah, let me remove this one. Let me assign this one to TR of A. Let me go with merge of TR of A. Hmm, let me go with TR of A. I'll just go with this one, comma B. Yep, so this is fine. Then what I'll do, I'll just go with a simple if condition. If this one, TR of A, TR of A, if it is not equal to 0, then let's go with a T parent of TR of A. So this one, yeah, let me assign this one to the A. Finally, the parent, so this one of A, yeah, is equal to 0. I'll just go with a full of A, and let me assign the R to A. We are done with this part successfully. Yeah. Else, right, if B is having the higher priority, then B becomes the root. For that also we have to write. So let me copy this particular line, or if I write here, this has to show actually. Again, TL of this one. Let me change the this one variables. TL of B is equal to merge of this one. What do we call A? Right. So let me remove this one. A comma. This one will be TL of B actually. Yeah, this is fine, I believe. Yeah, we are done with this part. So let me write the simple if condition, one more if condition here. So if TL of B, if it is not equal to 0, then T parent of this one TL of B itself, let's assign this one to the B. We have successfully done that one. Yep, so this is fine. Now I'll just go with a T parent of B. Yep, if it is equivalent to 0, so T parent of B will be assigning this one to the 0. Then pull of B, and let's assign R to B. Yep, so we are done with this part. Finally, let's return the variable R. Let's return the variable R. So let me format the code once. Yep. Now we are done with a merge method as well. Next, let's move on with a get root method. Get root method, because we have to walk up to the parent pointers to find the root of the tree, right? So this is nothing but equivalent to the representation or representative of the component. So I have to write the get root method. We have to make use of the, or we have to write the get root method at any cost. So I'll just go with here. I'll just come out of this one entirely, this method. So I'll just go with static int. So let me go with get root of this one parameter x. Yep. So within this particular method, I'll just go with a while loop. While, so I'll just go with a t this one parent of x. If it is not equivalent to 0, then x, I have assigned this one to the parent of x. So this is fine. And finally, all I'll do is I'll return x. Let me return the x. So I'll just come out of this one entirely. Now let me do one thing. Let's move on with the further things. So we have to make first here this one, make first in the sense when I said we have to make first in Euler tour tree. The Euler tour is circular sequence. We know this one, right? If you know the algorithm, Euler tour is nothing but the circular sequence. Make first, what it does, it rotates the virtual node to start, or V node to start actually. So this is needed before linking to this one Euler tour trace. So V's tour virtual tour starts at the vertex V. For that also we have to write the method actually. I'll just go with static here. So let me go with void make first. Yeah, let me go with int V node. Yep. So within this particular method, first thing I'll just go with a split before this one, split before of V node. Yeah, so this is fine. Then let me go with merge of split R, this one split right as well as the split left actually. Yep, so this is fine. We are done with this particular method. So let me format the code. Next, let's move on with the further things. Now, let's go with this one, ETT node mapping. ETT node mapping in the sense Euler tour tree mapping. For the Euler tour tree mapping, again we have to go with certain this one variables, as well as we have to consider certain data structures. Let's map the vertex to the ETT node. Yeah, I'll just go with a static here. Int. So I'll just go with this one V and nothing but V of vertex into level is equivalent to the ET2 node for that vertex at that particular level. So I'll just consider the variable Vn here, and also let me go with here int. Let me go with node to this one actually vertex. Yeah. So this is also fine. Next we have to go with the edge node storage. For the edge node storage, I'll just go with static. So let me go with a hash map here. Let me consider long as well as int. So this is fine. I'll just go with a variable e nodes here, and let me go with new hash map. Why this is showing? Anyways, new hash map. So this one is fine. Let me consider hash map once more. So I'll just paste this one over here. Hash map of long, and instead of int, let me consider integer. Yeah, array is not required. Integer. Instead of the e nodes, I'll just go with a level. Yep. So I'll be going with a level. So we are successfully going with the edge key as well as the tree edge, right? So these two things we have considered. Now let's go with a non-tree edge storage. So for the non-tree edge also we have to store somewhere. Let's go with a non-tree edge storage. So I'll just go with static here. So this one will be array list. static array list. So let me go with long. Yep, let me go with the long here. So this is fine. Let me go with NTE list. When I say NTE list, nothing but non-tree, this one, what do we call non-tree edge list. Yep, this is just the variable that we are considering. Now let me consider the hash map again. So I'll just go with hash map. This time I'll just go with a long. Instead of the same thing here, I'll just remove this one. Instead of the int, let me go with a integer. Yeah, as we'll be dealing with the integer, I'll just go with a NTE level. Along with the NTE, I'll just go with a level. Yep. So this for this one we have to go with new hash map. So this is fine. Yeah, this is fine actually. Yeah, NTE level. Next, what we'll be doing. So this is nothing but the NTE key along this one, nothing but NTE key along with its current level. For that, we'll be making use of the NTE level. So this is fine. Next, we have to go with a tree edge list as well. For tree edge list, I'll just go with static here. So let me go with the array list. This one, yeah. Let me go with the array list. So let me go with long. Let me go with long here. Why this is showing? So caps lock. Okay. I'll just go with the long. Let me mention the arrays. Let me go with a variable tree list. Yep. So this is also fine. After going with the tree edge list, this one considering the variable, then let's move on with the edge key encoding. When I say edge key encoding, so let me go with static here. Long for the edge key, I'll consider ek. Let's consider two parameters. One is u and another one is v. Yeah. So this is fine. So within the this one edge key method or the ek method, if suppose u is greater than v, in that case what we'll do, so I'll just assign t to u, then u to v, then v to t actually. Yep, so this is also fine. Let me come out of this one entirely. Then what I'll do, I'll just return. So let me go with the long. Yep, u into, let me go with 1 followed by 4 zeros. So this is fine. 1 plus v. Yeah. So this is nothing but the this is unique since v is less than or equal to this value, right? Accordingly with the question. So we have considered this one. Now after returning, so I'll just come out of this one entirely. Now let's go with some variables, some more variables actually. So I'll just go with static int edge u. So I'll just go with a long k. Yep. So let me return something here. Return. So I'll just go with int of k by the value actually. Yeah. So same thing. Let me copy the same thing and make the necessary changes that is required for the v. Right. So I'll just paste it over here. I'll just make this one ev. So this is fine. Long key remains same. Return int. So this also remains same. We need the reminder. So I'll just make use of the modulo. So this is fine, I believe. Yep. So we are done with these two methods actually, EU as well as the EV respectively. So we are just decoding the vertex U here and we are decoding the this one vertex V. These two things we have finished with these two things. Now let's go with a ETT link. When I say ETT link, it is nothing but edge tree tour. This one, what do we call? Edge tree tour link. We will be linking U and V in the ETT at the level 1. Then we'll be inserting two edge nodes actually, forward as well as the backward. That we will be doing. And finally, Euler tree tour for path U to V. These three things we'll be doing within the ETT link method actually. So I'll just go with static here, void. So I'll just go with ETT link. So this is fine. Let me go with three parameters, U, V, nothing but edge U, edge V, and L respectively. Now I'll just go with make first here, make first of Vn of U as well as L. Right, so this is fine. We are done with this part. Next, let me go with a make first here again. So I'll just go with Vn of V and L respectively. So this is also fine. Then let me go with long k equals here edge k of we have to pass two vertex, nothing but e this one U and V respectively. Right, so the first one, make first of vn, this one u, l and vl, whatever we have written, we are just rotating the u's tour, so u is first, and we are also rotating v's tour, so v is first. So after finishing these things, let's move on with the further things. Nothing but here in this case, I'll just consider the variable oc. Yeah, variable oc, I'll just go with e nodes here, this one, e nodes dot, I'll just go with the compute if absent. Yeah, compute if absent. So I'll just go with k comma x. So this is provided by the hash map actually. Yeah, if you know the hash map. Yep. Uh, only when the key is absent, then we'll be adding this one to the creating the key, and then we will be adding that one to the value basically. So I'll just go with k equals new this one int of max, instead of the max n, I'll just go with a max log here, right? Max log into 2. Yep, into 2. So this is fine. Let me close this one, yeah, or else we'll be getting the error. It will throw error. Now we have to consider the forward edge. So let's consider two edge direction nodes, forward as well as the backward, as we are dealing with the this one. What do we call? Undirected this one graph actually. So let me go with int forward. So I'll just go with a new node here. This one. Let me pass false actually, not true. This is fine. And also let me consider back. So let me call new node of here as well. Instead of true, let me go with a false, boolean value false. So here this one OC of not forward actually, I'll just go with L into 2. So this is fine. I have assigned this one to, let me assign this one to the forward. Yeah. For assigning this one to the forward, I'll just go with the forward, and I'll just go with OC of L into 2 plus 1. This one, let me assign this one to the backward edge actually, or the, yeah, backward actually. This is fine. Next, let's move on with the further things. We have to go with the root of use this one, Euler tree. What do we call that one? Euler tour tree. And we have to go with the root of v's, this one, vertex v's, Euler tour tree. So for that, I'll just go with ru equals, let me call the get root method here. I'll just go with a vn of u and l respectively. So this is fine. And one more thing, let me copy this one and let me paste it over here. So this one will be vn of v as well as the l respectively. Right, so this one is fine, I believe. V and L respectively. So instead of the RU, I'll just change this one to V. So this is fine, I believe. We are done with this part almost actually. And after going with the root of use Euler tour tree and V's Euler tour tree, we have to join actually. Euler tour plus forward plus this one virtual tour plus this one back. Not virtual tour actually, vertex V. U tour plus forward, V tour plus backward, accordingly with what we have considered, variables that we have considered. So I can just write it on this way. Merge of, merge again of, again merge. I'll just use here. So this one will be RU, comma, forward. So this is fine. And then I'll just go with the RV here. So this is also fine. Finally, let me go with the back actually. For the back, I'll just go with the BCK. Yep, we are done with this part. Let me format the code so that the code looks good. Now we are done with this method as well. Now we have to go with a Euler tour tree cut, which is one of the important methods as well, right? So within the Euler tour tree cut, we will be removing the edge u comma v from the ETT at the level 1 as per the algorithm. Now after removal, ETT looks like A plus forward plus B plus backward. So from the previous step itself, we know A plus forward plus B plus backward plus C, right? So after the cut, A plus C will be one component and B will be another component. Yeah, A plus B will be one component, and sorry, A plus C will be one component and B will be another component. So how can we write that one in the form of code? So let me go with static here, void. So I'll just go with a Euler tour tree cut actually. So let me go with cut here. I need three parameters. One is U, another one is V, and another one is L actually. Yeah, so within this particular method, first thing, let me go with the parameter K equals EK of U and V respectively. Yeah, so this is fine. Next one, let me go with OC here. OC equals, I'll just go with the E nodes dot this one. dot get of a. This is also fine. And finally, let me go with the forward. I'll just go with a forward, nothing but fwd. This one will be OC of L into 2. So this is fine. I'll just go with back. This one equals OC of L into 2 plus 1. So this is also fine. We are done with this part. So next we have to ensure the forward edge, whatever we have considered, comes before the backward edge in the sequence. For that, again, we have to write the code for that. I'll just go with position forward. So I'll just assign this one to position of, so let me go with a forward. Yeah. So I'll just go with a forward here. So we haven't written the position, this one forward as well as the position backward methods yet, right? So just give me a second here. 1 second. This is huge actually. The code is huge, no doubt. So we haven't written the position forward as well as the position backward, right? So let's do one thing. 1 second. So we'll be going with the position of actually. We haven't written the position of this one, right? Method yet. So let me do one thing. I'll just come out of this one. So I'll just write the position of method so that we can use it over here, right? So let me go with static here, int position of here. So I need one parameter, nothing but x, right? So I'll just assign the position to the t size, this one, t size of TL of x actually, t size of TL of x, this one. Yeah. So this is fine. Next, let me go with the while loop here. So this one will be t parent of x. Let's check if it is, whether if it is not equal to 0, then let me assign p to the t parent of x. This is fine. And if I'll just go with a t right actually, nothing but tr of p. Suppose if it is equivalent to x, not p actually. Yeah, if it is equivalent to the value x, then let's not return anything here. Then let's go with position equals position plus t size, this one, t size of TL of p plus 1. So this is absolutely correct. We are left with only one thing. This step is nothing but we are just adding the parents left as well as parent if the x is the right child. If x is right child, then let's assign x to p. It's as simple as that. Now let's return the position. Yeah, we have to return the position. So let me format the code so that the code looks good. 1 second. Just give me a second here. Yeah. Now this is fine. Let's continue. I'll just copy this one, where we have left. So we have made use of the position of here, this one within the ETT cut. ETT cut in the sense Euler Tour tree cut. Yep. So this is fine. Where we had left actually position of forward. So let me copy the same thing for the, or let me type this. It show. I'll just go with end position back equals position of backward. Yep. So this is fine, I believe. We are done with this part. Now let me write the simple if condition. If suppose position forward, suppose if it is greater than position backward, then in that case what we have to do, let me assign t to forward. Yeah, this one, t to forward temporary variable. We are swapping here, right? So then forward to backward, forward to backward, what we have considered bck. Yeah, so this is fine. Finally backward will be assigning this one to the temp variable. Yep. After this step, let's do one thing. Let's move on with the main thing. So we have to get the root of the entire combined ETT, and we have to go with the position of the back, this one backward edge in the sequence. These two things we have to do. For getting the root, I'll just go with root here equals, let me make use of get root here, get root of this one forward. Yeah, forwarded. So this is fine. Then let's do one thing. We have to get the position of the back in the sequence, backward edge in the sequence. For that, I'll just go with the pbck. I'll just go with the position of, again, let me make use of the method position of which we have already written. So I'll just this one pass the backward edge or the bck. Now we have to split off everything of the back position, nothing but we have to extract the back node as well as the C. That's what we have to do. For that, I'll just go with a split K. Yep. And let's this one. Yeah, let's pass the parameters here, root as well as the back. So this is fine. Now we are left with only one thing. Left is nothing but it is equivalent to the A plus forward edge plus B, right? This is for the left side. For the right part, it will be backward plus C, right? Backward plus C after splitting actually. So for that one, I'll just go with int left equals, let me go with a split L. So this is fine. And for the right part, I'll just go with a RIGHT, right part. So let me assign this one to the split R, this one. Yep, it's as simple as that. Now let's do one thing. We have to remove the back node from the front of right part. For that, I'll just go with a split K here. So this is fine. I'll just go with the right part, this one, the second one. Let me select this one, right part, comma, 1. Yep. After this, we are removing the back node from the front of the right part. For that, let me go with a int back node. So I'll just go with a back node here. Let me call the split L here. Yep, along with the split L. So I'll just go with let me do one thing. Yeah, let me assign the C to this one. I'll just make use of the capital C here. C to split R, right one. Yep, we are done with this part. Now what we'll be doing, we have to split the left to separate A and B. So I'll just go with a B. Let me go with a forward equals position of this one. Position of, so I'll just go with a forward here, right? So this is also fine. Then I'll just go with a split K. Split K of left as well as the B forward. Yep, so this is also fine. And finally, I'll just go with int A equals split L, nothing but split left. So I'll just go with forward and B. So let me go with a forward and let me go with a B equals split R. Yep. So this one split R. Yep. So we are done with this part as well. Now let's remove the forward node from the front of the forward and B actually. For that, again, let me call split K here. This is fine. Split K. I'll just go with a forward and B this part as well as 1. And one more thing, I'll just go with a forward node. Yeah. So let me assign this one to the split L again. And let me assign B to the split R. Let me assign B to the split R. So this part is also almost completed. So this one, let me go with a capital N instead of the small here. Camel case. Now let's reconnect A and C as one component and B stays alone as other component. So this one as I have we had discussed this one earlier itself while writing the ETT cut method. Actually, before writing the ETT cut method, I would so what we were doing. So what we'll be doing within the ETT cut method had said earlier itself. So we, as I've said, we'll be reconnecting this one A to C. We'll be connecting A to C as one component and B stays alone, right? Accordingly with what I have said. So for that, I'll be writing merge A comma C. Yep, merge A comma C. So we are done with this. And finally, I'll just go with OC of L into 2. Yep, let me assign this one to OC of L into 2 plus 1. OC of L into 2 plus 1. Let's assign both to -1 here. It's as simple as that. Now we are done with this, but let me format the code so that the code looks good. Now we are done with this particular method. Yep, and we had written this one position of as well, and we have made use of this particular method within the ETT cut. Yep, we are done with this particular method as well. Now we'll be moving on with the further things actually. Now we have to go with the connectivity queries as well. So in the input they have given con 1 to 5, nothing but connectivity. So we have to query from 1 to 5. So they have given in the input 1 to 5 thrice, right? So after doing certain operations, we have to this one query. For the connectivity query also we have to write the code actually. Yeah, we have to query, right? For that also we have to write the code. So let's move on with the further things. Yep. So we are going step by step accordingly with the algorithm what we had discussed. We are going step by step. Now I'll just go with static. Let me go with a boolean. I'll just go with the connections. L. So here let me go with parameters. We need vertex V, nothing but the edge U to V, vertex U, vertex V, as well as left, as we are going with the left connection or the connection left. So we'll be needing these these three parameters, U, V, as well as the L. Suppose if the value, if U equals V, in that case we have to return true. So this one we have already discussed. Then let me return, I'll just go with get root here, get root of let me go with a Vn of U as well as L respectively. Yeah, of L respectively. This one will be checking with get root of Vn of V as well as the L. So this is fine, I believe. We are just checking same ETT root is equivalent to the same component or not, right? So I'll just come out of this one entirely. Now we are done with this method as well. Next, let's do one thing. Let's move on with one more method named connected. Yeah. If you remember the algorithm, we had it on the connected method. Yeah. So I'll just go with static here, Boolean. So let me go with connected method. Yep. I need two parameters. One is U and another one is V. Yeah. So let me do one thing. I'll just return here. So let me return. So this one will be this one method name actually. What are the parameters that we have made use of? Actually, U, V, and L. Let's initialize this one to the 0. Yeah, initially the value will be 0. Yeah, we are done with this part as well. Next, let's move on with one more method, nothing but component size. See, size of the component containing V at the level 1 will be equivalent to the size of its Euler tree by 2 plus 1. Yeah, and each vertex appears twice per the edge in Euler tour ETT. But we will be making use of the t size as we have went with a variable tsc. We'll be making use of the t size of the root directly. So I'll just go with static here. I'll just go with int. So let me go with the component size. This one comp sz. Yep. So this is fine. Sorry. Yeah. So this one I need two parameters. One is v and another one is l. Yep. So let's return something. I'll just return here. What shall I return? I'll just go with a t size of let me go with a get root of vn, get root of this one vn of v and l respectively, right? Vn of v as well as l respectively. So this is fine. Yep. This is also fine. Let me come out of this one entirely. We are done with the component size method as well. Now, let's move on with the further things. Yeah. So I'll just go with a set on method. Set on method is nothing but we have to set on flag, nothing but NTE ownership. NTE ownership in the sense non-tree edge ownership. Yep. Why this is required? So basically we are setting T on of Vn of VL equals F. Then we will be propagating uh, pull basically whatever the method pull that we have written up to root to the uh, to root actually to maintain the TNT, right? So we have to go with the non-tree edge. If we are searching for the non-tree edge after the removal of the edge, we have to assign that one from the starting node at particular level where we are considering to the node where it is assigned. So for that also we have to write the code, right? So for that, let's write the code now. So I'll just go with static void. So I'll just go with the set on here. So let me go with certain parameters here. I need V, I need L, as well as I need F actually. Yeah, and F. So this is fine. So within the set on method, first thing I'll just go with ND here. So this one will be Vn of VL respectively. So this is fine. Let me write the simple if condition because no change is needed if the on this one ND is equivalent to the F, as I've said, T on of Vn, whatever we have considered of ND is equivalent to the F already, then no change is required, right? So I'll just write here if C. I'll just go with the T on here. Yeah, this one of ND, if it is equivalent to F, then I'll just give return. Then let me go with the T on here again. This one T on of ND. Let me assign this one to F again. Let me go with a variable x and let me assign this one to the nd, and the same thing we have done this one previously as well. So let me go with a pull of x. We have to pull for the optimization purpose. I'll just write here while loop while t parent of x, if it is not equal to 0, then x equals t parent of x. So this is fine. And again, what we have to do, we have to go with the this one pull of x actually, pull of x. So this is it for the method set on actually. This is it for the method set on. The last line from here to here, this while loop, basically what we are doing, we are just pulling all the way to the root. That's what we are doing. Now we are done with this particular method as well. Let's move on with the further things. So we have, yeah, so this is fine. We have to link or add the edge, right? So we have to link or add the edge in the sense, so the non tree edge that we have considered, we have to link that particular edge from vertex source vertex to the destination vertex, whatever we are considering. For that one also we'll be writing the node, for that one also we'll be writing the code named link actually. So I'll just go with void, the method name is link, I meant. So I'll just go with int u comma int v. So this is fine within, sorry, yeah. So within this particular method, what we'll be doing, I'll just go with long k equals ek. So I'll just go with a vertex u and v respectively. And let me go with a simple if condition here. If not of connected, sorry, if not of connected, this one, if not of connected, we have to consider vertex u and v itself, right? In that case, we don't have to stop here. Within this if condition, we have to consider the spanning tree edge, nothing but we have to link the ETT at the level 0 or Euler 2 tree at the level 0. For that, I'll just go with E level. This one, we have already considered the global variable E level, right? So I'll just go with that one, E level dot put. What we have to do, put, we are making use of it from the hash map actually. Yep, K0, we are updating the values, right? K, K0. So this is fine. Now let me make use of the tree list variable. I'll just go with U as well as the 0. What we have to add basically, we'll be adding K, right? So then let me go with tree list of V0. This time it will be tree list of V0 dot, I'll just go with a add of K. So this is also fine. Finally, I'll just go with the ETT link. Yeah, this one basically. Yep, let me make use of the ETT link, which we have already written. Let me pass the parameters here, 1, 0. Yep, so this is fine. Let's write the else here, right? Then we have to consider the non-tree edge. We have to record it and no ETT changes needed, meaning no Euler 2 tree changes needed. In that case, I'll just go with a non, this one, tree edge level, this one itself, dot put of K0, dot put of K as well as the 0. Yep, so this is also fine. Next, I'll just go with NT list actually. This is also fine. NT list of U as well as 0. This is also fine. Dot add of K, so this is also fine. I'll just go with the NT list of V0 dot add of K. Yep, so this is also fine. And let me go with the set on of U0 true actually. So this is also fine. Yep, true. And let me go with set on here. Let me go with the set on. So I'll just go with V0 and true. Yep, so this is also fine. Yeah, what we have done at the last, this one last line, we are just marking the NT ownership in ETT. NT nothing but non-tree edge ownership in the Euler tour tree. Yep, so we are done with this part. Let me come out of this one entirely. Let me format the code once. Yeah, let's move on with the, so that we can move on with the further things. So this is it for the link method. Now we have to remove the edge, right? If NTE, so remove edge, why we will be going with that, basically we are cutting, removing edge in the sense we are cutting itself, right? So removing edge, we have to remove the particular edge, nothing but which consists of the vertex u and v. If non-tree edge, then we have to just remove from the list, right? So if it is a tree edge, then we have to find the replacement. We have to find the replacement. Yep. So for that, I'll just go with again static. So we have to remove or cut, right? So for that, I'll make use of the variable, this one method name cut. So let me go with the parameters u as well as the v. You would have already guessed, as we need to cut or remove, we'll be making use of. Quite obviously, we have to remove the edge. We need the parameters u and v itself, right? So this is fine. Let me go with k here. So this one will be ek of u comma v respectively. Now this is also fine. Let me write the simple if condition here. If not of e level, yeah, e level dot, I'll just go with the contains key. This one contains key of k. In that case, what shall we do? Let me, yeah. If it's an NTE or the non tree edge, we will simply remove from the NTE lists. So for this one also we have to write the code. So this is huge. I'll just go with the NTE level here. This one NTE level dot remove of k. Yep. So this is fine. Next, let me go with the NTE level. Sorry, this time I'll just go with the NTE list of UL actually, of U as well as L. I'll just go with the remove of k. Again, let me go with the NTE list this time as well. We have to do the same thing as we are dealing with the undirected graph. We have to do that one for the reverse as well, VL as well, right? Dot remove. So of k. Next, let me do one thing. Let me write the simple if condition here. If NTE list, so this one, if NTE list of what we have to consider basically U and L, right? This one U and L. Instead of the size, let me do one thing. Let me delete this one. Let's check whether it is empty, right? Is empty, then let's do one thing. I'll just go with the set on method that we have already written. Within the set on, we have U as well as L, and we will be going with a false actually instead of the true. We'll be setting this one F to false actually. Yep. So the same thing let's do for the V as well, right? So I'll just go with the if condition. If NTL list of VL is empty, we'll set on VL false. So this is also correct. Yep. Finally, we have to stop here. So I'll just go with the return keyword. It's as simple as that. Now let me come out of this one entirely. Now what shall I do? So if it's a tree edge at the level, this one LVL, I'll just go with the LVL here. So this one will be E level. Where is E level? This one. E level dot remove of k. Yep, dot remove of k. So this is fine. I'll just go with the tree list. This one tree list of u as well as the level. Dot remove of k. So this is correct. And let me go with this one. This time it will be v actually. Same thing we have to do, right? So I'll just go with a tree list of v level. Dot we have to remove. We have to go with a remove of k. And finally, we have to cut the Euler to tree or the ETT at all the levels from 0 to level. For that, as we need to cut at all levels, cut ETT at all levels, let me make use of the for loop here. I'll just go with the for here. Int L equals 0, L less than or equal to level, and let me increment the L, right? So here, I'll just write here ETT cut. So this method we have already written. All we have to do is we have to, one second. So yeah, let's continue. What are the parameters that we have here? One is U, L as well as the V. Let me pass the parameters. Now we are done with this part. Yep, it's very simple. Now all we have to do is we have to try to find the replacement edge at the each level from level down to 0. Yeah, accordingly with what we had discussed, we have to write the code for that one as well, right? We have to find the replacement edge at each level, right? So for that, I'll just go with a level. So this one, instead less than or equal to level, I'll just consider greater than or equal to this one 0. Yeah, not level. So I'll just we are just going with a, basically we are going with a reverse iteration here. We are not going with this one. We are going with a reverse iteration. That's it. Yep. So this is fine. So let me remove this one. And within the for loop, first thing, I'll just go with a SU here. So this one will be comp SU. Comp size we have considered, right? Component size actually. Component size of, let me pass UL here. So this is fine. And for the SV, let me assign this one too. Again, comp size of V and L. Yep, so this is fine. Next, let me go with small. Yeah, let me go with a variable small. Let's check whether SU is less than or equal to SV. If it is, then let's display U, else we will be displaying the V. Yeah, and now we'll be going with a variable large. Let me go with a small here. This is fine. If it is equivalent to U, then let's display V, else we'll be displaying U. So this is fine. Yep. Let me come out of this one entirely. Now all we have to do is we have to promote all the tree edges on the smaller component up one level, right? So this is nothing but the Holm-de, this one, what do we call? Lichtenberg invariant we call, right? So we call this one as HDT invariant, right? So I'll just go with if, I can just write it in this way. If L plus 1, if it is less than max log, yeah, this value itself, then I'll just go with promote tree. So let me go with promote tree actually. So we haven't written the promote tree, and we will be going with a find replacement as well. Find replacement as well as the promote tree method, we haven't written that one. Yep, let's write that one, and then we can just come back here and we can just use those things here, right? Promote tree as well as the find replacement. Find replacement for promote tree. So I'll just let me erase this one. I'll just come out of this one entirely. Now, just give me a second here. Let me write here static void. Let me go with promote tree here, right? So this consists of two parameters. One is V and another one is L. So why we have went with a promote tree? Let me explain you this one. So this is nothing but the promote tree edges. All the tree edges at level L in the V's component. We are speaking in the V's component, right? In the V's component, get promoted to the level L plus 1. HDT invariant that we have considered here, basically we are going with a HDT invariant, right? HDT invariant is nothing but edge at level L is equivalent to both the components with a size greater than or equal to 2 to the power of L. So let me write this one. Let me write the code. You'll understand this one. Let me explain this one step by step. First, let me assign the root to. We have already written the get root. So get root of Vn. So this one will be V and L respectively. So this is fine. And so I'll just go with the array list. This one, array list of integer. So this is fine. Array list of integer. So let me go with the word equals new array list. So this is also fine. Nothing. We don't have to pass anything here. So, and I'll just go with a collect words as well, right? So I'll just go with the collect words. So we have to write the collect words to make use of the collect words here. So first, let me do one thing. Let's write the collect words here. Then we can just come here and continue the code actually. For that, I'll just go with the static. So I'll just go with the void here. Let me go with the collect words actually. So I need two parameters. One is X and another one is, so I'll just go with the array list. Let me make use of the array list here, array list of integer. Yeah, instead of the widths, I'll just go with a out. Yep. So this is fine. So first thing, so let's go with a simple if condition. If X equals 0, we don't have to do anything. We just have to stop. So then we have to consider left self as well as the right. Left, so I'll just go with a, let's go with a recursion or the recurse. So here, this has to be collect words, man, not widths actually. I'll just go with a, I'll change here as well. Yeah, so this is fine. Now collect words of TL of X as well as the output is showing. So this is fine. So I'll just go with if. Now we have to go for the self. Suppose only if the vertex node is present, right? So I'll just go with a t here, t vertex, this variable. So I'll just go with the x. So now I'll just go with out dot add of node to vertex, nothing but this one, node to vertex of x. So this is also fine. Next, what we'll do, I'll just go with the collect words, this one. Yep. Let me add tr of x as well as the out. Yep. So we are done with this part. So this is it for the collect words actually. Yeah. Let me format the code so that the code looks good. Now we are done with this part. Let's make use of the collect vertex within the promote tree. So promote tree where we have left. So we have lot to write. So let me make use of this one. Correct words here. So let me do one thing. Let me pass the root as well as the words as parameters. So we are just collecting all the vertices in V's component at the level 1 actually. After successfully doing it, now let's move on with the for loop. So for within the for loop, I'll just go with the int sv of words actually. Yep, of words. Then let me go with one more for loop here. So I'll just go with for. So I'll just go with long here. Yep, long k of let me consider new here. Let me go with array list. Array list, we don't have to consider long here. Anyways, so I'll just go with within the parenthesis. Let me go with the tree list. This one, yes, tree list of. I'll just go with the sv variable sv as well as l. Yep. So this is fine, I believe. So within the for loop again, what we'll be doing this time. So let me go with a simple if condition. This is nothing but the stale entry. For the stale entry, I'll just go with if not of e level, this one, if not of e level dot contains key. So this one contains key of k. Then what I need to do? So this one or sorry or yep, or e level dot get. So this one will be e level dot get of k not equal to l. So this is fine. Somewhere I have done something wrong, man. I have messed up something. So contains of k I have closed here. So instead, let me close here. Right. This is the only mistake. Yep, so this is fine. In that case, we have to skip. So I'll just give the continue keyword that is provided by the Java. So after the stale entry, let me consider the variable EU and let me assign this one to the EU of k. So this is fine. And let me consider the variable EV as well. So I'll just go with EV of k for this. Yeah, let me assign this one to the EV of k. So this is fine. If not of connection, this one connection L, this one. Yeah, this method we have already written. The parameters that we have to pass is EU, comma V and L. Then if not of if the edge is not present in the V's component, in that case we have to skip. For that, Java provides for skipping. Java provides continue keyword. I'll just give this one. So this is also fine. Next, what we'll be doing. So we have to promote the edge to L+1, right? Meaning we have to update the level and we have to move from tree list of L to the tree list of L+1, right? For that one, I'll just go with E level. So this is simple. Yeah, this is simple. I'll just go with a put here. So this is fine. Put of k, comma L+1. Yep, k, comma L+1. Then I'll just go with the tree list. This one. Yep, tree list of EU and L we will be considering, not SV. We don't have to go with a variable SV. We have to go with a vertex U actually. EU, this one, and L dot remove of k. So this is correct. So let's move on with the further things. Again, tree list, this time EV and L dot remove of k. Yep, so this is correct. Next, what we'll be doing, I'll just go with tree list. We have to update, right? For that, I'll just go with tree list of EU. This time it will be L+1, right? Instead of removing, we will be adding, right? So I'll just go with add of k. The same thing we will be doing for the this one vertex V as well. EV L+1 dot add of k. right? So this is fine. Finally, what we'll be doing, we have to link the ETT at the level n plus 1 as well, right? So for that, I'll just go with the ETT link. This method we have already written. All we have to do is we have to pass the parameters. So this consists of EU, this is fine, and we have to pass EV as well. Yep, EV as well. Instead of L, it will be L plus 1, and we have added EV, so I'll just remove the V. So this is it for the this particular method, actually promote tree. It's as simple as that. Now we are done with the promote tree method as well. Let's move on with the further things. Yeah. Where we have left. Yeah, promote tree we have written, right? So one more method, we will be using this one, find replacement edge method as well, right? So within this particular method, cut method actually. For that one also, let's write the this one code, and later we can come back to the this one method cut, and then we can just make use of promote tree as well as the find replace method within the cut method actually. Yep, let's continue with the same. I'll do one thing. Let's do one thing. I'll just go with, so find replacement edge. So what does this method do actually? So we have to search all the non this one tree edges in the smallest component at the level 1 for one that bridges to the large component. So in simple terms, we have to search for the this one. What do we call replacement edge, right? So I'll just go with the static. We have to search for the replacement edge, right? So non-tree edge basically. Yep, if we have successfully removed the this one, what do we call the edge? Actually, we have to check for the entire graph that whether this one replacement edge is present or not. Yep, nothing but the non-tree edge is present or not. For that, I'll just go with find static boolean here. Let me go with find replacement. So this is fine. Let me go with three parameters. One is small, as I've said, small. So let me go with a large as well. So I'll just go with the large, and I need L as parameter. Yep, these three parameters. So within the find replacement method, first thing, let me assign the root to. So let me give here get root of, I'll just go with Vn of small into L. So this is correct. Next, let me consider the array list here. Array list of integer. Yep. So I'll just go with the words, this one new URLs. So this is fine. Next part is nothing but, again, let me go with the collect words here. Nothing but we have to pass root and words. The same thing, similar to this one actually. See, these two are almost similar. This one. Again, we have done the same thing here, right? So this is fine. Tier of X. So this one is fine. Within this one, we don't have to go with the right of X actually. We have to go with the root, sorry, not the get root as well. We have to go with the root, just root, and we have to go with the out actually. So here we haven't considered, one second, what did I do? Equals 0 return. So why am I coming to this one? One second. So I am in the this one collect words method, right? So I completely am out of this one. One second. Yeah, so root and vertex. So this is correct actually. I have left this one here, right? So let's continue with the same. Sorry. I'll just go with int sv of words. Vertices actually. So this is fine. Within the for loop, first thing, I'll just go with one more for loop here. So this time it will be same thing, long k of new array list. So here, instead of the tree list, what am I gonna do? I'll just include NTE list. This one, yeah, I'll include NTE list of SV as well as the L. So this is fine. Let me, yeah, within the for loop, let's include EU as well as the other. So first thing, I'll just go with the variable EU. So I'll just go with EU of A, EV. So let me assign this one to the EV of A. Yeah, so I'll just go with other. Let me go with other. So I'll just assign this one to the EU. So it is SV. Let me go with EV. It's display EV. Else if it is false, then display the vertex U actually EU. Yep. So this is fine. So this is for the endpoint, not in a component, right? So this is fine. Let's move on with a simple if condition here. I'll just go with the if. So I'll just give connection L. Let's go with the other. So yeah, other as well as small is not required. I'll just go with the large here along with the parameter L. Yep, so this is fine. Yep, so within the if condition, so if we have found the replacement, then the particular NT or the non-tree edge, right? So the NT now becomes the tree edge at the level 1. Yep, that we know from the algorithm. So for that one, I'll just go with the NT level dot remove of K actually. Yep, so this is fine. Then I'll just go with the NT list here of let me go with the NT list here. NT list of EU into L dot remove of this one K, remove of K. So this is fine. This is fine. Let me go with the NT list. So this one is also fine of EV and L. So this one, for this one also we have to write the code, right? So as we're dealing with the undirected graph. And now let me go with a simple if condition here. If NT list of EU, if NT list of EU and L, so we are just checking is empty, then let me go with the this one. What do we call? Set on method that we have already written. Set on consists of EU L as well as we'll set this one to the boolean value false. F to the boolean value false. Now let's do the same thing for V as well. I'll just go with the if here. NT list of EVL. If for the is empty, I'll just go with the set on of instead of the other, I'll just change this one to the EV. Yeah, EV L as well as the false. Now let me come out of this one entirely. Now what we are going to do? So I'll just go with the E level here. So this one E level dot put. So this one will be we don't require L plus 1. I'll just go with the K and L respectively. Then let's go with the tree list here. Tree list of EU and L. Tree list of EU as well as L dot add of K. So this is fine. Again, we have to do that one for the V as well. So I'll just go with tree list of EV to L dot add of K. So this is also fine. Then let's go with a simple for loop. For loop because we have to link at all the levels from 0 to the levels that we have actually. If suppose if it is 4 levels, 5 levels, we have to add the link at all the levels. For that, I'll just go with a for loop link levels. I'll just go with a variable LL here. So equals 0, LL less than or equal to 1 and LL plus plus. Yeah, so this is fine. I'll just go with the ETT link here, this one. So what are the parameters that we'll be making use of? EU, EV as EU, EV and the LL. Yep, so this is fine. So the next one would be let's return true. Yeah, let's return boolean value true. So now let's go with the else. Else, so if the NT non-tree edge connects two nodes in the same component after the cut, then we have to promote it. So for that also I'll be writing the if condition within the else. So I'll just go with if here. If I'll just go with L plus 1 if it is less than max log. So I have already considered max log here. Then in that case, I'll just go with the NT level. Yeah, NT level dot remove. So let me remove K. Yeah, let me remove K. So this is fine. So I'll just go with the NT list. Let me go with the NT list here of EU. Yep, of EU into L. So this is fine. Just EUL. So I'll just go with the remove of K. Remove K. So let me go with NT list. This one EVL. So for this one also we have to write actually. Yeah. So this is also fine. Again the same condition if NT list of this one EU is empty. So I'll just consider this one as EU. First let's consider for the EU. Then we can just go with the EV actually. U into L. Is empty, then we are just going with a set on of EU, L as well as the false. Then let me go with if NT list here. So this one EVL is empty. Then we will be considering EVL as well as the false. Yep. So this is also fine. Then let me go with the NT level here. This one NT level dot put of K comma L plus 1. Yep. So here we are doing the same thing as this one we have done here, right? So now this step is complete. Next, let me go with the NT list here. Yep, NT list of this one. What do we call? EU into L plus 1. Yeah, dot add of K. So this is also fine. Then the same thing let's do for the another this one V as well. So this one will be not NT level 1. NT list. So this one will be EV into L plus 1 of dot add of K. Finally, let me make use of the set on method here. Set on, what are the parameters that we have? You can just check. I'll just go with the EU L plus 1 here, and also let me include true. Yep. So the same thing we have to do it again for the vertex V. I'll just go with a set on of EV, comma L plus 1 and true. You would have already guessed this one. Let me format the code so that the code looks good. Now we have successfully written find replacement as well as the promote tree. So now let's do one thing. Let's make use of the promote tree method within the this one cut method actually that we have written this particular method. Yeah. So we have already written the if condition here. Suppose if L plus 1, if it is less than this one, what do we call max log? Yeah. So what it indicates basically, one second. Yeah. So basically we are promoting all the tree edges in the smaller component to one level up actually. Yeah. So this is nothing but the HTT or Lichtenberg-Thorup invariant actually. So I'll just write here promote tree. Yep, promote tree of let me consider small. Let me pass the parameter small and L as parameters. Next, let me go with a simple if condition here. If I'll just go with a find replacement that we have just written this method. Yeah. So let me go with find replacement. Within the find replacement method, let me pass the parameters small, large, as well as this one L. Yep, this is also fine. Small large L. In that case, we have to stop. So I'll just make use of the return keyword. Yep. So this is fine. We are done with this particular method. Yeah, we are done with this particular method, and we are done with the problem as well. Right. All we are left is we are left with this one. What do we call the input output part? Actually, that we will be writing within the what do we call main method. So this code is huge. Anyways, 331 lines. Okay. So I'll just come here. So this is fine. Let's move on with the main method actually. Yeah. So for the main method, I'll do one thing. Instead of typing this one, let me paste this one and let me explain. Yeah. So that's small actually. That's related to the complete. That's completely related to the input output part. Let me paste that one and let me explain you. Just give me a second here. So let me do one thing. I'll just paste this one over here. So this one you can just ignore. Usually I check this one in the this one Java Online Compiler. So that is the reason I have given unchecked. So this is fine. So first thing, so let me explain this one. So I've just pasted from this one, only the main method actually. This is completely related to the input output part. So I didn't want it to type this one. Already the code is very huge actually. Anyways, so let me explain you this one. Buffered reader string tokenizer. This is completely related to the input output. So this is related to the fast input and string tokenizer, right? So this is fine. N and M is nothing but we have to read the number of vertices and number of queries. In the question, they have given number of vertices here 5 and 11. This is nothing but the edges. We have to read that one. For that, we have written N and M respectively. Pool. So this one now from int pool to this one, whatever we have considered from here line number 339 to 346, whatever we have written, we are just allocating the flat arrays minus size that is equivalent to vertices into log plus edges into 2 into log plus buffer. So that's what we are doing with the by considering the pool actually. So TL and T size, we have already done that one. We have assigned this one to the size pool actually. So this is fine. So VN is nothing but whatever I have written here, VN. Vn is nothing but the vertex plus node ID at each level. So this one node to vertex, the whatever I have written, this part is nothing but node ID to the vertex number. NTE, so we know this one. NTE list is nothing but NTE or non-tree edge adjacency per vertex per level. And finally, we are going with a tree list. Tree list nothing but tree edge adjacency per vertex per level, right? So this is fine, I believe, until from here to here, line number 339 to 346. Next, let's move on with the further things. So this for loop, nested for loops we have written, right? So these two for loops, what we are doing with this within these two for loops, we are just initializing the each vertex at each level. Yeah, we are initializing the each vertex at each level with a fresh ETT in the sense Euler to tree vertex node. For that we have already written the code. You can just check this one. We have made use of the NTA list, and this one we have to store somewhere, so we are making use of the array list for IL, and this one twice actually, and then VN of IL. So this is nothing but vertex node at the level 1, this one vertex node at the level 1, and finally we are recording the reverse mapping, right? So we are recording the reverse mapping. So this is it for the this one from 348 to line number 354. Next, let's move on with the string builder part. So string builder part, this one is completely related to the this one input output. Basically this is related to the output, so we have to accumulate the output for the fast input output. So this is completely related to the input output. Yeah, so this is fine, I believe. So here what we are doing, the final line system out print of SB, nothing but string builder, whatever I have given here. So this is nothing but the single print for all the output as we are making use of the string builder, right? So this is fine. They have asked us to go with the this one. Display the output in the format yes or no. So this one we have just appended this one to the connect. We will be checking whether it is connected or not, which is written within the connected method. The edge is connected or not. We are querying, right? Accordingly, we'll be querying accordingly with the this one edge that they have given, that they'll be giving within the input. Connected of 1,5 they have given in the input, right? So if it is connected, then we are printing S. If it is not connected while querying, then we have to print no. That's what we have written here, right? So add for the insertion, remove for the this one, what do we call, for the deletion actually. Then we are linking here, then we are made use of the cut. Actually cut is nothing but removing. We are checking whether after removing edge, whether the this one, what do we call, uh, non-tree edge is present or not. If everything goes well, if the graph is connected, in that case we are just giving. If it is connected, we are going with S, and if it is not connected, then we are going with no. This A and B, we are just reading the inputs, right? So the string tokenizer, and this is fine, I believe. Yep. So this is it for the coding part. Let me format the code once so that the code looks good. Now we have one error. What is the error? Missing return statement. Where is this? Find replacement, we are just going with a boolean. We don't need return statement actually here, right? So 1 second, find replacement itself, right? mm, or we have to go with within the find replacement, we are checking whether we have the replacement or well. If everything goes well, we are giving true. Okay, yeah, let me do one thing. If uh, we cannot find the replacement, in that case let's give false. Yeah, so this is also fine. Now the error is gone actually. So now let's do one thing. Let's try to run the code. Yep. I'll just come here. We come here. Let me run the code. So it's asking for the input. So let me open the Chrome. So I'll just copy this one. This is extremely huge, man. Debugging becomes difficult actually. Let me copy this one and let me paste it over here. We have some error. Cannot load int array because C is null. Okay, that's the only error we have. Okay. 1 second. So let's see where we have done mistakes actually. Let's come to the split K here. I'll just come to the split K. 1 second. We have written at the beginning itself, right? Before, yeah. This okay. So this is fine. Within the else, let's come to the else here. So within the else, so we are checking for if split are not equal to 0. So I have copy pasted the same thing, or here I have to check actually split L, not the split R actually. Split L not equal to 0, then uh, T parent of split L. So we have assigned this one to X. So this one I thought it showed the this one what we call suggestions. I pressed the tab. I believe. So that's the so this one I have corrected. So this is fine. Next, let's do one thing. I'll just let's check whether any other things are wrong actually. Yeah, give me a second here. I'll just come to the set on here. ETT cut. This is fine. These are all the things that we have already written. So I'll just go with set on. In the set on actually we have written the while loop. While t parent of x. So this one is not equal to 0. So I have assigned here x equals t parent of x. So this is fine. Then pull of x, right? So one second. So let me do one thing. I'll just add the this one parenthesis. This one lar bracket here. So this is fine. Yep. Instead of here, so let me close this one over here. So let me format the code so that the code looks good. So let's check. We have done some mistake over here. So this is fine. Within the let's check within the cut actually. Link is fine. Let's cut within the let's check within the cut actually. I made use of the tree list here. So this is fine. Twice the tree list, and then we are just going with a for loop. The for loop we are just going with int l equals 0. So this is fine. L less than or equal to level and L plus plus. So we are just going with a ETT cut, so which is absolutely correct actually. And we have passed U. So oh yeah, so here in the parameters we have given U, V and L, not U, L and V. Yep. So this is fine. This is also one of the things that we have to cut. Then that we have to correct actually. That is also fine. Then let's move on with the this one find replacement method. Promote tree is fine. We don't have to touch promote tree. Then within the this one find replace method, we have written nt level here. Nt level. So this is fine. Nt list we have made use of it twice. So here, so let's go with the if condition. What I have written nt list of EU. So I have to go with EU, U and V respectively. Yes, U. So this one, let me change this one to U. So now this is fine. Dot is empty. Set on off. So this one will be EU ln false. Yeah. So this one will be EV ln false. So this is correct now. Yep. So this is also fine. Then finally, let's move on with the for loop here. We have made use of the tree list twice. Then within this one, we are checking for the level, right? So mint mm, level. So this one we have initialized this one with a 0. This is fine. Less than or equal to, oh, this is not 1. Less than or equal to level actually. We have to check for the level, and level we are incrementing. So this is fine. ETT link EU, EV as well as the well double L. So this is also fine. Finally we are returning true. So this is fine, I believe. Now let's check if anything wrong. All right. So this is fine. I believe everything is correct now. Yep, let's do one thing. I'll just run the code, whatever we have written. Yeah, we have selected the same thing, right? So let me run this one again. Come here, one second. Let's open the Chrome. So within the Chrome, let me copy the input again. I'll just to this one IntelliJ. Let me paste this one over here. Now if I hit the enter, yeah. So now we are getting the output no, yes, no, yes. So these were some of the mistakes actually. Yeah. So the code is heavy actually, extremely lengthy. So there were some typos, 3 or 4 typos that I had to correct. Yep. So apart from that, everything is fine. One thing, the parameter, this one order actually that I had to change, and 2 or 3 this one. Mm, 2 or 3 typos actually that I had made mistake. So that I had to change. So this is fine. We are getting the output no yes, which is absolutely correct. Now let me do one thing. I'll just copy the same thing. I'll copy the entire thing actually. So let me copy the entire thing. So let me close this one, the algorithm part. Let me copy the entire thing. I'll just open the Chrome. There is an option here, submit solution. Let me click this one and let me paste this one over here. So this is not required, I believe. Yep. So this is only required for the IntelliJ part. So this is fine. And within the SPOJ, we have to make sure that we are giving the method name as main. So this is fine as well. So public, let me keep this one public. If we get the this one, what do we call? If you get the error actually, let me remove the public. Let's see. So instead of the ADA, I'll just change this one to the Java. Where is Java? Hotspot. So let me change this one and let me hit the submit button. So yeah, let's wait for some time. Yeah, so this one here, you can clearly see it's showing compiling, right? So let's wait for some time. So yeah, you can clearly see that. Wrong answer. Why? So let's check for the answer. 1 second. So 1 second. What did I paste actually? It is showing here. 1 second. So let me paste this one again. I don't know what mistake. Just let me remove this one. This is not required. So yeah, instead of this one, we just change this one to main. So this is fine. Yeah. Now Java, we have already chosen Java actually. Now let me hit the submit button. What was the mistake last time? I didn't. So now if I hit, yeah, now there is a solution actually. Last time it was only showing. So I thought, I think I have submitted only the this one. What do we call? Uh, Java part actually. So this time it has to get passed. Let's see. So you can clearly see here the verdict that we got here is AC accepted, right? You can clearly see here, right? So this one, let me open this one. Yeah. You can clearly see here. Wow, this is huge, man. 376, almost 400 lines of code. Anyways, I hope the implementation of this particular algorithm is completely clear, man. Holm-de-Lichtenberg-Thorup algorithm, right? So let me open here. One. Let me hit the ID on hit. On it. Yeah. You can just check the code here clearly, right? So whatever the code that we have written works absolutely correct. Yep. So the only thing is you have to know the implementation. You have to know the Euler tool tree, which we have discussed. The algorithm Euler tool tree, we have already discussed that one within the 150 algorithms playlist. You can just check that one. It's easy, man. If you understand the algorithm, it's easy. So Euler tool tree is actually easy. I'm not gonna say no. It's actually easy. If you go through the algorithm once, you'll get to know. I can assure you that. Yep. You can just go through the video that is present in the tree-based algorithms playlist or 150 algorithms playlist in the both actually. We have discussed that one same thing. We have discussed the same algorithm Euler to tree with the help of this one within the by making use of the Java programming language. You can just check there. Yep. So this is fine. Um, and also, yep, Euler tool tree is the main thing actually. Yep, we have segregated into different methods. That's the reason it is big. The code is big, no doubt. So we have segregated this one clearly actually, starting from the split k. This one split before whether it may be merge. Get root, we have to get the root. Yeah, for getting the root and ETT link Euler to this one Euler to tree link. Then we have went with the ETT cut. Yeah, this one for the cut actually. Then we have went with the connection L connected. We are checking whether the edges are connected. For that, we have written connected, component size, set on. Yeah, we have made use of the set on most of the times, right? So that this acts as this helper method we have made use of several times. Link, yeah. Then cut, actually I had explained you this one. Cut, promote tree, find replacement, yeah. And then finally collect vertices. We have to collect vertices. This we have made use of it within the other method, right? Cut, I believe. Collect vertices I have made use of within the cut method, I believe. Yep. Finally, we have written the this one, what do we call, within the main method we have just written that's related to the input output part mainly. Yep. So this is fine, I believe. Yeah, I hope the Holm-de-Lichtenberg-Thorup algorithm is completely clear, right? So the code is little bit lengthier when it comes to the implementation. The algorithm is fine. It's not that much lengthy. You can just go with a pure algorithm as well. While discussing the algorithm, we have went with a simplified version, right? So we went with a Euler tour, this one, what do we call, tree. Basically, we went with insertion, add, remove, as well as the connected. For the querying, actually we went with the connected method within the algorithm as well. So we went with the this one, a bit simplified version. Here within the connected method we have just tweaked so that the complexity actually changes a bit here. This is not pure completely because else log square n. Accordingly, with the algorithm, if we are considering theoretically, it has to be because of log square n. We have already written the algorithm and we have already discussed the same actually. So here, whatever the algorithm that we have implemented here, mainly what do we call, uh, uh, this one, HDT algorithm that we have implemented, right? So that one theoretically the time complexity is because log square n. So here we have tweaked within the connected method, so it changes a bit. If we go with a pure implementation, it will give us this one, what do we call, TLE actually. Yep. So that is the reason I have tweaked a bit in the connected method. You can just check. Yep. Compare the algorithm as well as whatever we have written within the this one, whatever we have implemented within the problem. Yeah, you can just check that. So here it becomes actually big of m into log square n. Yep. Instead, it would be big of m into log square n. A bit of tweak actually. Yep. So this is fine. Now we are left with only one thing, nothing but discussing the complexities for the code that we have written. So what would be the time complexity? Just give me a second here. 1 second. Yep. So what would be the time complexity here for the code that we have written for this code? Yeah, the time complexity. So we have written add remaining. So this one connected all three actually, right? So we are inserting, removing, as well as we are going with a query, nothing but the connected. So for the add, it is this one, big of log square n amortized. Yep, big of log square n amortized for the add. For the remove as well, it is big of this one. So I'll just mention here, big of log square n amortized. So for the remove as well, it is big of log square n amortized. Yeah. So what is for the query? So for the query or the connection as well, it is big of logarithmic n. Yeah, it is big of logarithmic n. Yeah. For the add, it is big of log square n. For the remove, it is big of log square n. And for the connection or the query, it is big of log n. Uh, big of log n. So overall, as per the tweak actually that we have made, it would become big of m into log square n. M log square n, or m into log square n. So this is the time complexity actually. This is the time complexity for the code that we have written because m into log square n. So what would be the space complexity here? The space complexity would lead to big of n plus m, yeah, into log n. Yeah, the big of n plus m into log n. So this is the space complexity actually. Yeah, the overall space complexity would lead to big of n plus m into log n for the Euler tour tree nodes that we have made use of, and adjacency lists per level. We will be storing adjacency lists per level, right? So for that, it would lead to overall space complexity would lead to big of n plus m into logarithmic n. So what would be the time complexity and the space complexity both actually? For the time complexity, it is overall time complexity would lead to big of m into log square n, and for the space complexity, it is big of n plus m into logarithmic n. So this is it for the time complexity as well as the space complexity. Yep. So I hope this one, what do we call? I hope the algorithmic complexities part is completely clear, and I hope complete Holm-de-Lichtenberg-Thorup algorithm is completely clear, right? So we have got the opportunity to implement the particular algorithm, HDT algorithm, within the this one for this particular problem actually. So let 1 second. Yeah. So let me remove this one. Yeah. We have got the opportunity to implement the same thing, the algorithm, the entire algorithm within this problem. Actually, I'll just give you the link of the problem if you want to check, or if you want to implement the same algorithm, go on, and you can just try implementing the same, right? So, yep. So this is it for the algo and this one algo implementation within the problem. So for now, this is it. Thanks for watching, guys.